All right. All right, folks, what do we got here? 11 people today? I think most of you know me by this point. Bernie Missoula. I'm the Director of Health and Safety for the IFTI, industrial hygienist practicing for 25 plus years, etc. We're going to be covering air monitoring. Ooh, I have the wrong one up. Hold on, folks. We're going to be covering air monitoring today. Why don't we start by introducing who we've got here and why are you taking this class?
Mike Mareshi from 1280, local 1280, District Council 35. I'm on the call from Pembroke, New Hampshire. I'm taking the class because as an instructor, the more you could add to your knowledge base, I think the better serve the members.
Okay. I think Mike, this is what, our maybe 10th class together? Getting there.
Yes,
Oh, no.
sir. I sign up for everything.
Side.
How you doing? This is Nuno Portella. I'm with the FTI of New Jersey, District Council 711. Much like Mike was saying, basically just gathering up more information and taking more classes so we can bring that information back to our members and better serve them, better inform them.
Okay. Welcome once again. What else we got?
From the training center, safety coordinator. I'm pretty much doing the same thing, just, trying to gather more information. The more information you have, the better you are.
Daniel Valdivia, DC 30. Same deal here, an instructor, making sure we give the right information to our students and making them more aware of the testing that's involved.
All right, welcome. And where is DC 30? What does that cover?
We're the suburbs of Chicago, Aurora, Illinois.
Oh, okay. Okay. Welcome. What else we got?
I'm Jeremy Allen with Local 1887 out of Boston, District Council 35. I'm the industrial instructor and same thing, just extending my knowledge base and making sure everything's up to date.
All right, welcome. Good to see you again, Jeremy.
You too.
Joe Terkowski here with DC 14, Chicago, industrial instructor here. Just staying up, current and fresh. This is a really good refresher going into big lead classes, C3 and stuff like that that I have coming up. So,
Great.
and also I just wanted to see what the new topic is on that and stuff like that.
Sounds good. Anybody else?
Tim Yost.
David Arbayo. Yeah, go ahead, Tim.
Okay, thank you, David. Sorry.
That's
Tim
right.
Yost, DC 35, industrial painter by trade, and I do health and safety classes. And like everyone else said, I'll take everything I can get.
Yeah, my name is David Arbayo out of DC 30 as well as Danny. So I'm a safety instructor, apprenticeship. So just trying to learn a little more about the safety issues.
Welcome. Is that everybody?
Yes, sir. This is everybody. I reached out to the guys in Florida, and see if they would be able to join us. But this is everybody. This is where we're at.
All right. So so this is air monitoring. So this is one of the things that industrial hygienists do a lot of, and there's some pretty hefty goals of this class. Unfortunately, this is one that would really be best if we could do it in person, because there's a lot of hands-on activities that I built for the end of this class. We're not going to be able to do those, obviously. It's my hope that I'm going to be offering an OSHA 521 industrial hygiene course. So it's a 5-day course as I teach it. It's a 4-day as OSHA does it, but as I do it, it's about 4.5. And it's adult ed based. It's 4 unions, and this is one of the modules in it as well. So you'd be able to get OSHA credit for that course, 521. So hopefully in the future, I'll be able to offer something like that. And you can at least revisit this with the actual hands-on activities and such. But nonetheless, we do have a paper-based one that we can get through, but I've got a lot of places for discussion, things like that along the way. So here's some of the goals that we've got, and I know it's a lot of them, but there's air monitoring is so important to protecting our, our health and safety, especially if you're doing some kind of a career, over a lifetime. So we want to be able to state why air monitoring is important for worker health and safety, explain the importance and limitations of air sampling worker exposures, list 4 different types of units used to quantify chemical concentration, list 3 benchmarks to compare air monitoring results to. So just because we do the air monitoring, if we don't know what those values are, it's not very helpful to us. Now it's it's on the employer to make sure that that's communicated to workers. But if they don't understand what it is, you can see why that could be an issue. That's why it's important to understand some units and understand what the values actually mean. List at least 5 elements that should be in an air monitoring plan. Describe the use of at least 4 types of equipment used to evaluate chemicals in the air. Define calibration, intrinsic safety, lag time, response time, and maintenance. Explain the limitations of colorimetric tubes and use them to determine the concentration of a contaminant. So this is one of our objectives that's tied into doing a hands-on activity, which we won't be able to do, but use an FID and PID or other available direct reading instruments to determine concentrations. Again, this is part of a hands-on activity. Identify sampling media, flow rate, sample volume, analytical method, and interferences for a given compound using the NIOSH or OSHA method for that chemical. Use a calibration device to adjust the flow rate of a personal sampling pump. Again, this would be a hands-on activity. Place one of these pumps with a sampling device on a worker. Calculate a time-weighted average when given multiple concentrations with different exposure times. Again, this would be part of our hands-on activity. And provide 3 questions to ask an industrial hygienist in the field to make sure that they're competent. So unfortunately, the number of industrial hygienists in the United States is going down pretty sharply. I hate to say it, but I'm one of the older industrial hygienists at this point, which is crazy because I'm only 46. Many of my mentors are retiring. There are not a lot of programs that offer industrial hygiene anymore. So a lot of times you might get, somebody who's acting as a health and safety professional on site, but they're not an industrial hygienist. They're not familiar with sampling, especially the nuances of it. And we're going to talk about why that's important. So one of my goals for this class is so that you can go and you can ask one of those health and safety, people that are out there about sampling. Give them some questions. And if they get defensive, if they can't answer them, that's got to throw up a couple red flags. Because as I've said before, anytime somebody talks to me about industrial hygiene, it makes my day. So, right. So they should be able to answer these questions for you. And you have a right to. You have a right to ask questions about sampling that's done, what the results mean, what they found, etc. Under the OSHA Act. So, all right. So a little group activity here. What is the purpose of air sampling? So since we've only got a handful of people, we're just going to keep it in one group here. So what do you think? What's the purpose of air sampling?
Need a baseline.
What do you mean by a baseline, Mike?
We need to know before we do any work what the atmosphere is at that moment.
Good.
So that if something goes up, we're able to calculate the difference.
Yep, and that can be really important, especially for confined or enclosed spaces. If you're concerned about differences between background and what you might be introducing into that air that might be above that. So yeah, that's a good reason. So we want to look at background levels. What else?
PPE
We need to
requirements.
know.
Yeah, David, PPE requirements. That's a good one. What else?
Make sure we're within the standards of OSHA and also just checking to make sure the effectiveness of our engineering controls.
Yeah, so was that Joe that answered there?
Yeah.
Yeah, so you're right. I hate to use that one, right? But it's one of the reasons why we sample, to make sure that we're meeting those OSHA standards. But As I've said before, the thing I don't like about exposure limits are they're basically legal ways to poison a worker. Those of you who've taken the toxicology course with me, we know that there's a lot of chemical exposures that have no real safe value because we haven't been able to determine that yet. So even though we have an exposure limit, it might be a carcinogen, and we don't know that there's any safe value for that. But yet benzene, which is a carcinogen, has, it's got a PEL, it's 1 ppm. So yeah, so that's one of the reasons. And that's usually the one that the employer wants to know, unfortunately, right? Not what's the best practice, and every now and then I have employers that really want to go above and beyond. Some federal agencies or states require that, like the Department of Energy requires that contractors use the most protective exposure limits. Good. What else? So
we need to know what we're getting exposed to in multiple different environments or work areas.
Yep. Good. Good. So, there's a lot of these things, reasons. You guys hit most of them, adjust PPE, revise controls. So I have this as our general, hierarchy of controls, right? So we want to make sure that, it's not just PPE, but maybe we have to use ventilation, something else to get that exposure down. As, was stated, meet exposure limits. Some of them are laws, some are guidelines or recommendations, and then create or revise SOPs. So have you ever done a job, like a job task, and you found out that you were producing something or something was going wrong, and then you noticed that and you were able to revise what you were doing and it corrected that issue? Has anybody ever had, experienced something like that?
Yep.
Right. So this is a good way to figure out that we need to do that. So you might not have, I guess the luck or the luxury of maybe seeing with your own eyes a need for changing controls, right? Let's take drywall sanding. Just because you don't see, a dust cloud there doesn't mean you're not getting appreciable amounts of that inhaled into your body. You'd want to be able to sample for that, right? So if you can identify these things that we can't detect with our senses, right, the naked eye or smell or something like that, then it's important to be able to adjust how we're doing that work and maybe change that process up. Inhalation is the most common way chemical exposures happen, right? We mentioned this when we cover exposure routes. When we did the toxicology course. If you look at that pocket guide, right, it's got 677 different chemicals in it that have exposure limits through airborne exposure. So this is something that we're always very concerned about. And just to revisit why is it that we're most concerned about inhalation exposures? Remember what I said about, we talked about like what the surface area of the lungs look like, right? If we were to take all those air sacs and bronchial airways and flatten them out, they would cover about a tennis court. So there's a lot of surface area there for chemicals to contact. Also, there's very thin cell membrane walls, right? Because that's our gas exchange reason. So it can, the lungs can really get beat up, and it's a great way for chemicals to get into your body. So there's many OSHA regulations that require worker exposure assessment or air monitoring. Now, exposure assessment and air monitoring, can be a little different, even though they kind of mean the same thing. You'll hear me use them interchangeably. Typically, an exposure assessment means I'm more able to statistically or definitively tie air values to a worker. As opposed to air monitoring, it could be very general. It could be, area monitoring at a fence line or a perimeter just to see if there's fugitive dust escaping your work site and affecting neighbors. Maybe it's oxygen levels in an area and there's no workers in there, but I'm concerned about it. So those two phrases are used interchangeably, but they do mean different things sometimes. So, we got specific chemical regulations, right? Benzene, asbestos, lead, cadmium. There's a number of regulations where it specifically spells out you've got to do, exposure monitoring for workers, and it's got to be done in a very specific way. There's no wiggle room in these kinds of things. Any chemical that's got a PEL or a TLV, a threshold limit value, or a NIOSH-REL, right? We look at doing it that way. And then there's some OSHA standards that require air assessments in general, right? Two ones that you're probably familiar with are the HAZWOPER standard and confined space. Has anybody taken a HAZWOPER course before? Okay, Mike, I see, okay. And, you might recall that there's very specific situations that the regulation requires an employer assess the air, right? And confined space, same thing. Has anybody taken a confined space class or done any confined space work? Okay, same thing, right? What are requirements for confined space monitoring? What are some general rules of thumb that we have to follow? I shouldn't say a rule of thumb. It's something that we have to follow.
Permits?
What's that?
Permits?
Yeah, you have to get a permit, and in order to fill one of those out, what do you have to do?
You gotta take readings on your
Yeah,
oxygen gas.
before or after a worker goes in.
Prior to.
Right, prior to, and then continuously, right? So there's requirements that tell us generally how to assess as well if you've got certain standards. And this is all stuff that an employer is supposed to know, but a lot of this ties right into almost all work that IUPA team members do. Depending upon what trade it is, chances are there's going to be air monitoring that's a part of that work, even if it's something like trade show work. Do you think folks are members who do trade show work? Is there any air monitoring that you think might needs to be done? Might not be as excited as bridge blasting or something, but how about general indoor air quality, right? These are some things that we know that indoor air quality can make occupants pretty sick. So I can't, like I said, I can't think of any IUPA trade where air monitoring wouldn't touch somehow. Air monitoring helps you determine if the air you breathe is safe, right? So this is an excerpt right out of the HAZWOPER standard. Air monitoring shall be used to identify and quantify airborne levels of hazardous substances in order to determine appropriate level of employee protection needed on the site. So that's right out of a standard. And anytime we see that shall in a standard, means that employer has got to do it. It's not a maybe, right? HAZWOPER standard requires initial site entry and then periodic. So just like with the confined space standard, you got to make sure that it's okay for that worker to go in before they enter. And then as they're down there, you have to make sure that, the air is acceptable for them to be in while they're conducting their work. Site workers, whether it be on a construction site, in a facility, they're doing HAZWOPER work, they have to be able to understand air monitoring to a level where they can understand what the results of reports are and their personal assessments. Because remember, if a worker has personal air sampling done for them, they have a right to that data. And if there is an overexposure of somebody on the site, they have a right to view that data. So what do you think some triggers would be for when air monitoring would be required under any standard or any job site? What do you think some triggers are? You're muted, Joe.
Lead jobs?
Yep, absolutely. Lead, what else?
It was going to be a confined space.
Yep, any confined space. Yep.
Any job where there is any pre-job analysis done that shows that there is a potential of an airborne chemical or anything on that job site.
Good. And that's connected to an employer doing their due diligence, right? Doing what they should be doing, making sure that they've run down what the hazards are, identified them. And that's important because, if there's not a standard, but you're using a chemical, if it's volatile, if you're using it in a way that can get it up into the air and you can breathe it in, we want to be able to make sure that we can assess what that is. And it's required. It's required under OSHA. Good. And again, this will help you out because this is something that you can transfer on to all the students that go through your classes. You know, if they're constantly working around chemicals and they don't see any samples taken, if they never see another worker with, you know, a pump and a cassette on, or anybody with a handheld monitoring device, that should throw up a red flag. And that's an opportunity for them to go and have a discussion with their union steward there, right on site. Especially like with construction work. I mean, what do you think are some big construction job triggers where you'd know, you know, an employer would have to be doing exposure monitoring?
Sandblasting and paint removal.
Yep, sandblasting, paint removal, okay. What's something that nearly every construction worker is exposed to at some point in their life?
Silica.
Was that?
Mold.
Silica.
Yeah, I was thinking of silica. It could be mold too, yeah. But I was thinking of silica, something that we just got a standard for not too long ago, right? Good. So, you know, the monitoring may be required depending upon what's happening on the job site. Initial exposure characterizations, you know, this is a lot of times could be connected to one of those job hazard analysis or specifically to a, you know, a chemical standard like lead. Periodic monitoring, you know, if possible changes in the atmospheric conditions can lead to an exposure that's going to be really detrimental to that worker, like an IDLH, or, you know, an explosive atmosphere gets created or something like that. Work starts on different areas of the site. You know, this would be something that would be categorized under HAZWOPER. New chemicals are used, right? So maybe you're introducing something new now and work's already been going on, but now they have to assess what that exposure might be. If different operations or tasks are initiated or a work process changes. You know, what's an example of how your exposure could change if a work process changed? What do you think?
Well, you could, if you were going, removing paint by abrasive blast, and then you switch to like something else, like some caustic paste or something.
Good, good.
Two different processes.
Yep, perfect. That's a great example. One I was thinking of is you go from hand scraping to sanding, right? Or maybe you go from hand sanding to mechanical sanding, right? That's gonna probably change that exposure. Good. You know, and then work under a HAZWOPER or another standard that will lay out what those triggers are. Air monitoring results force a change in controls based on sampling plan action levels or regulations. So, you know, it could require continuation of air monitoring, change in PPE, different types of hazard controls, engineering controls, or, you know, maybe immediate evacuation. If you take the example of, you know, of your confined space, right? Now, it's a really good idea. It's not always required. Under some standards it is, under best practices it is, but to have a sampling plan. So, you know, it's a really good idea to have in writing what you're going to do to help you make it successful. You know, just like if you're, you know, going to be, you know, putting an addition on your house, or you're going to be remodeling your bathroom, or it's an exercise plan or whatever. If it's just in your head, you will probably forget things, you know, things don't go right. It's easier to miss steps. But if you've got that plan there, right, that's going to help you out. And for an employer's point of view, having a sampling plan protects them for liability. Because if somebody does get sick, they can, you know, pull that out and say, no, look, I did this exactly how others would do it, right? Other industrial hygienists, or it's how the EPA recommends I sample for asbestos, or OSHA, or whatever. So it actually helps the employer out as well. But having a written plan is a good idea. And this is something too, when it's created, that workers should be a part of. Again, you know, there's no way in hell I'm going to understand, you know, to the level that you all do, what the common day-to-day tasks of different IEPA team members are. But I would want, you know, some of them, you, somebody else in the field that I meet, to say, hey, you know, Bernie, you know, I know you're sampling for this, but look, when I do this kind of work, you know, on this day, I really think I'm getting a high exposure. Thank you. I'm going to want to find that out, right? And so I'm going to want to adjust my sampling plan to be able to capture that. So it's really important to get worker involvement in doing this kind of thing. Any comments or questions so far? All right, so these are just 4 common units that are used with exposure, in air monitoring. What you're going to see is reported out in results. You've probably seen these before. Parts per million. This is a volume per volume unit. Milligrams per cubic meter. So this is a mass per volume unit. Percent is going to be, it could either be a mass in mass or a volume in volume unit. And then we've got fibers per cubic centimeter, right? So this is a number per area, concentration per area, if you would. All right, so let's visualize what this means, because I gave the example, you might not see what you're being exposed to. If there's a dust cloud or something like that, or a vapor cloud, boy, that's not good for you. But just because you don't see that doesn't mean you're not, potentially inhaling something that is toxic for you. So, if we had 0 here, these here are just, clear jars of water, and then they mixed in some dirt. In parts per million from 0 to 10,000, 10 ppm, 100 ppm, you still really can't detect it with your eye. Not until we get up to 1,000 can you start to detect it. Now, we could put some coloration in there, maybe try to change things up. It's still very difficult to detect things below 10,000 ppm in liquid with the naked eye. But this is just an example of how to visualize something like this. And if you look in that pocket guide, almost so many of those values, PELs for 8 hours, are less than 100 ppm. So again, just letting you know, you're not going to see it necessarily. Chances are you won't. So here's another example. It's a 55-gallon drum. 4 drops in this barrel is about 1 ppm. So it's just tiny, tiny amounts. How much is a gram? Because we use a metric system when we look at our exposure units. So 1 gram is about the mass of a pack of sugar. And the reason why, does anybody know why I'm using mass instead of weight?
I think people get a better visual when they see pack of sugar versus weight. They
Yep.
have an understanding of what they're looking at.
Yeah, so that's one of the reasons, like as a trainer, why I put these up here. But mass is independent of gravity. So if I took, this 1 gram sample and I say it weighs a gram, that's here on Earth. If I took it to the moon, it would weigh a lot less. But the mass of a gram is going to be a gram no matter if it's on the Earth, the moon, Jupiter, whatever. So when we're talking about concentrations, units of, something in air or something in water, we always use mass as our reference point, because it can change depending upon what the gravity conditions are. So here's some contaminants. You might not see them, right? So here is an example. This is on it's a penny, and this is 2 to 3 rice grains. You see how, so these are magnified. 5 to 6 human hairs are over here. So you can, if you can see it on the screen, these little lines, and those are asbestos fibers, which you can't see. Granted, our glasses, I know, but still, this is blown up under a microscope. So you're not going to be able to see 20,000 asbestos fibers distributed in the air. But you'd be able to see, 5 to 6 human hairs if you look really close and if the light catches it right. So again, it's so important to make sure that we've got our workers protected by someone who's responsible to do monitoring for them. All right, so let's match these substances up with some appropriate units. So if I've got organic solvent vapors up here, oxygen, asbestos, and silica dust, which one of these 4 typically is shown to us in percent?
Probably oxygen.
Oxygen.
Yep, good. Oxygen meter, right? If we're doing confined space entry, we got to make sure that we check that. How about ppm?
Solvent vapors.
Yep, very good. How about milligrams per cubic meter?
Silica dust.
Very good. And finally, we got our asbestos in fibers per cubic centimeter. And, you know, when a worker gets a report back, you know, they're going to have units associated with that number. And it's important that they understand what those units mean. I can't stand it when I pay, you know, to have samples sent off to a lab and they give me back units that I have to convert into something that's commonly used. That happens more often than I like. But you know, they might get a report back and they're not units that they're used to, so they have to make sure that they communicate. You know, even though I deal with kilograms all the time, you know, it's still not intuitive to me, you know, when I'm calculating, you know, how my power lifts are doing, you know, or my body weight. Because in wrestling and in judo and powerlifting, I have to fit into a weight class. And if I'm comparing myself to, you know, elite athletes, it's always in, you know, kilograms. Man, I still can't get it sometimes, right? So I have to calculate that back into pounds to see where I'm up against. So it's important that we have units that we can visualize and that we understand, just like we went back, you know, to that gram mass in the packet of sugar. All right, knowing that 1% equals 10,000 ppm, it's going to help you evaluate some exposure samples. So if we're taking volume to volume in air, right, that's what our parts per million is. It's important for us to know that 1% of something in air is equal to 10,000 parts per million. So let's figure out why that might be useful. So if the normal oxygen level is 20.9% and it's reduced to 20.4 in a confined space by toluene solvent, is this an issue if the safe level of oxygen is between 19.5 and 23.5? So you know, my reading is 20.4% of oxygen. So does that fall within this legal limit? Yep, that does. But what else do I have to be concerned about?
You got to look at the permissible exposure limit for toluene.
Right. And look what happened here, right? If my normal oxygen level is 20.9%, but I told you it's 20.4%, what happened here?
Something's displacing the oxygen
Yeah,
level.
exactly. Something's taken the place. So, you know, I can look at, you know, 0.5%, right? Because that's a difference here of toluene times 10,000 ppm. If that's what I spilled, that equals 5,000 ppm. What do you think of that for a level? That wouldn't be good. I don't think you'd be able to stay awake in that for much more than a breath or two. So, you know, go ahead.
I said, you're gone.
Yeah, you're exactly. So it's important to, you know, to use clues. So sometimes it's not going to be the greatest idea to wait a while to figure out what's going on. If you see that on a meter, you know, oxygen goes down or it's starting to go up. Maybe if you've got like a PID, which reads out in general, we'll look at that in a minute. You got to say, hey, something going on here, especially if you're working in a confined space or an enclosed area. I always will add enclosed area because although an enclosed area does not fit the definition under OSHA of a confined space, do you think you could still have some extreme exposure situations? Right, because you could be working in a closet. Is that a confined space? Not under OSHA, right? Maybe you have a small utility vault room. Not under OSHA, is that a confined space? But there's limited ventilation in there. You know, it's going to be able to accumulate. There's not a lot of area or volume in that space for a chemical to maybe spread out and get displaced. So we got to be careful. Ooh. So why is converting from parts per million to milligrams per cubic meter important? No, I gave the example before. Go ahead, David.
Because Nash Pocket Guide might give you one or the other one as a BEL.
Exactly. And in the pocket guide, you know, you might be familiar, sometimes they give a conversion factor. So you might want to go between one or the other. This is a general way in how you do it. It never changes. If you are looking for ppm, You'll take whatever the milligrams per cubic meter value is you've got, you plug that in. You multiply that by 24.45. And this is the molecular volume or the molar volume of air at standard temperature and pressure. So I remember some faces from when I did the chemistry class. So remember, gases or vapors are going to expand out and they're going to fill the space that they're in. So this is a general volume of air that would occur for what is 1 mole of, a mole is a defined amount of a chemical. Okay, so we take that defined amount and how much volume in air would that basically take up under standard temperature and pressure, which is room temperature and atmospheric pressure. And then we're going to divide that by the molecular weight of whatever the chemical was. And then you just would reverse it here if you want to find what the milligrams per cubic meter are, and you've got ppm. So you plug your ppm there, you put in the molecular weight for that chemical, and then you divide that by the molar volume of air. And this is just a quick way to do this. So quick group activity, convert the results to ppm and determine if the exposure is above the TLV, time weighted average. So we'll go through this and just click on the slides. This is something, again, if we're in a small group atmosphere face to face, we would be doing this together in our different groups.
Hey, Bernie, quick question. Are you going to make these slides available? Because you got a lot of good information on them.
Yes, sir. Yep. Yep.
Thank
so
you.
Usually, like Nicole and Manisha would usually upload them before, but I've requested that we wait until after I do, because sometimes I'll find something that I'm like, I wish I did it differently. So usually they'll do it now after I'm done with the class. So thank you. Yep. So results from the lab are 1.2 milligrams of benzene. So this is what an exposure was for a worker. We know that the molecular weight of benzene is 78.11. And benzene TLV for 8 hours is 0.5 ppm. Well, I want to figure out if I exceeded that. So we're just going to plug in the value, 1.2, which is what we got in milligrams per cubic meter times the molar volume of air, divide by the molecular weight of benzene. It's 0.38. And the TLV for benzene is 0.5. So we're good. So I was not overexposed to the TLV of benzene.
How do we figure out the 24.45? What is that number from again?
So this is the molar volume of air at standard pressure and temperature. It never changes for us. You're always going to use 24.45 in this equation, always. The only things that'll change are if you're given the milligrams per cubic meter or ppm. That's a variable that it depends what they measure. And then the molecular weight is going to be whatever chemical is you're trying to find to convert. So if it was benzene, you look up the molecular weight of benzene. If it's toluene, you look up the molecular weight of toluene, which I think is 90 something. And so that's how you go back and forth. Good question.
And then when we get these PowerPoints, is there instructor notes that'll kind of break that down if we forget?
Yep. Yeah, I have instructor notes in. I don't know, how much I have on this slide in particular, because I haven't looked at them in a long time. But if you ever forget something, just shoot me an email or give me a call. My phone's always open to you, or email.
All right, thanks.
Yep, absolutely. Air monitoring ensures that no one is working in an atmosphere which presents an immediately dangerous to life and health hazard. What's the definition of IDLH? How is that defined by NIOSH?
Immediately dangerous to life and health.
Yep. So what does it mean though? There's a pretty wordy definition. It used to have a time limit associated with it of 30 minutes, but it doesn't anymore. Basically what it means is that at that atmosphere, if a worker enters it, they're going to suffer either irreversible health effects or death. That's it. Immediately dangerous to life and health. You will suffer irreversible health effects. So in other words, you go in, you breathe something in, it's a lung toxicant, it damages your lungs, even if you're taking out the exposure, you've got permanent lung damage or you die. And these are some examples of IDLH conditions. 10% of the LEL. This is what the action limit is for that, because if it gets towards the LEL, you blow up. Oxygen is either below 19.5%, could cause you to pass out, or above 23.5%. That would lead to more aggressive burning, right? Because you have a high enriched oxygen environment. And then any of the IDLH conditions where there are defined exposure limit under a NIOSH, and you can find those in the pocket guide in that IDLH category. All right, so this is just a quick rundown of oxygen levels and why we need to evaluate them if we're working in confined spaces. 25% or so we're at increased fire risk. It's easier to have a flame. It's easier to have more complete combustion. This is our safe value here that OSHA says that we can operate in. At 16%, you're going to breathe faster. Your heart rate's going to go up. Why?
Working harder for you.
Yeah, that's right. I need 2 breaths now to every one where I was in a good atmosphere for oxygen, right? There's going to be some drowsiness. You might feel nauseous. At 12%, unconsciousness. And see, here's an example of why I like to hold off. I found that as I resized this graphic, I didn't realize I made this a hyphenated word, and that just looks awful to me. Anyway, sorry, I digress. 6%, you're dead. So again, very important that we look for oxygen if we're doing confined space entry, things like that. An exposure assessment or air monitoring plan should be developed by an industrial hygienist to promote effective monitoring of variable exposure conditions. So what does this mean, variable exposure conditions?
Could be different conditions where maybe you have an explosive atmosphere, or you have a lack of oxygen, or some sort of hazard.
Yep. Okay. Any other examples or thoughts?
Conditions that could change.
Yeah, Tim, why? Like, give me an example.
Well, if you introduce something that displaces oxygen, it's your oxygen level is going to change, go down.
Yep. Let's see. How about if you guys, let's say if you're using a coating that's got a lot of VOCs in it, so it evaporates pretty quickly, and you go from using it on maybe exterior walls or something like that, or inside at a big gym room, but then the next day you're using that same product, but you're in the hallways or you're in closets. Is that a variable condition?
Yep.
Yep. How about if you're outside on a construction site and you're still working with a lot of soil?
What about a compressor or a type of machinery setting off exhaust?
I couldn't hear you, Donald. You're very low.
What if there's a piece of machinery sending exhaust your way? Exhaust from a piece of machinery?
Yep. That would be a change of condition. What about if you're working outside, and one day wind's blowing around and you got a lot of silica dust flying around, the next day it's not windy, right? So it's important to have a plan to be able to capture this stuff. And again, some rules like the HAZWOPER standard or the confined space entry, or the lead standard, they require you to have an air monitoring plan so that it's in writing what's going to be done. You can evaluate airborne contaminants either real time, so you can actually have a device that's going to give you a readout of what concentrations are, or you have to collect it on some kind of media device, and then you got to send that off to a laboratory. You have to wait for results to come back to you. So here's an issue. So sampling only captures a snapshot in time, okay, for a specific condition related to the time of sampling. So like when I write reports, I always say, this is what I found at the time of the assessment or at the time of the inspection. You know, maybe somebody was moving a, you know, compressed gas cylinder through the hallway and they stopped for lunch and they left it there. It's not tied off to a wall or anything. They walked away and I come by for my audit and I happen to find that, right? That would go in my plan, that would go in my report because I found it. But it's not necessarily there the other days if I were to show up, right? So that's the problem with air sampling. I'm going to take an air sample on one day, hopefully for a full shift, maybe not, maybe it's maybe it's 4 hours. And I'm going to have to assume that that's a normal condition, but I might be way off, right? So let's look at this. This is called a Gaussian distribution or a bell curve. Many things in life, including exposures, typically fall in this kind of a curve. So if I were to take, thousands and thousands of samples, we would get this shape based on, what my exposures were. So if I put like a mount down here, like, concentration, 0 ppm, 50 ppm, 100, whatever, right in the middle, about 40% of the time, I'm going to be getting, whatever this value would be. This is the true value here. I have no idea though if I'm at the true value. So I could go and sample on any given day for the exact same person doing the exact same task. There is a true value of what they're exposed to, but I don't know if that's the true value of what they're exposed to every day, right? So the problem lies, let's say I go and I sample and it happens to be a day where you're doing something that's abnormal. And maybe you hardly use any chemicals that day. And so your exposure is very low. And so I'm going to get something down here, right? Am I close to the truth? Nope. In fact, I could be really underserving that worker by reporting what I found that day because it's a really low number. And the other, 300 days a year, that number is a lot higher. Same thing could be true up here. I could end up, showing up and taking some samples from somebody at a really unique day where they're using lots of chemicals, and they normally don't do that. It's a requirement for some hazardous chemicals that I sample for worst case scenarios, right? Like lead, asbestos, cadmium. I need to find the tasks that are going to most likely produce the highest exposures for those workers, and I have to make sure I sample them. So, this can be a problem if I'm only going to show up and take a couple samples. Ideally, if I could show up, a couple times a month, maybe a couple times a quarter, and take a bunch of samples, I would start to get closer to this right here, the middle of this peak. But if I'm only going to go and I only take one sample on any given day, I have no idea where the hell that sample is going to come. So statistics can help sort of determine how close that sample is to the true value, but it's not foolproof and you still have to take enough samples. So the rule of thumb is the more samples that I can take, the closer I'm going to get to that worker's true exposure. But does that happen often?
No.
No. Why not, do you think?
Most of the contractors, when I work with the industrial, all the assessments are done at high risk tasks. So sandblasting, power tooling, stuff like that. But, they've got to pay for that stuff to be done. And then on top of that, a lot of the guys, they got to wear this thing right in front of them, while they're doing their work. And sometimes it's a pain in the butt. And I've seen guys hang it on stage and go do their work. You're not going to get a perfect example of a person's full day of work unless they're wearing something constantly every day throughout the whole job.
Right. So it's time consuming, it's expensive.
Yep.
It can, create a burden to the workers wearing them. In most cases, I found, especially I always communicate to somebody I'm sampling as to why I'm there and what it means for them personally. In almost every case, people have been, thanks, because it's just something the employer's got to do. Put me through this. No, actually, this is going to help you out, and this is how. couple times I found some people that did like what you said. They take it off, they'd hang it somewhere, and I'd be like, oh, thanks, man. You know, or they'd be funny and blow cigarette smoke in it, stuff like that. But more times than not, you know, it was basically, you know, a contractor, an employer, hey, look, this is the amount of time I want you here. I don't want to pay for that much. It's expensive. The lab's expensive. That's true. But safety is not cheap, right? To do it the right way to protect workers. And sometimes, you know, if you sample less than what a standard of care would be, you might have a false sense of security as an employer. And then OSHA comes through and they do it the right way. And they say, hey, man, what happened here? You said that you took these samples and this is what you're saying is documented, and you don't have anybody in PPE, the engineering controls aren't, you know, whatever. Big difference between what I got and what you got. Why is that? Well, geez, I only took, you know, I only sampled 2 workers for half a day. Ugh. So there's issues with sampling. One of the things that I like to do is if there is a hazard there, let's just control it. And then let's use some air sampling to see how well I did controlling the hazard, as opposed to, you know, rolling dice and crossing my fingers that workers aren't being exposed. But we still have to try to set up a sampling plan with some good statistical weight behind it. And there's a method for doing that. NIOSH wrote a report back in 1997, which is when I was born, about how many samples you have to take depending upon how many workers you have, and if they're doing similar work tasks, things like that. It's burdensome, it's encompassing. But, you know, Olympians don't win a gold medal, right, for taking the easy way out. So, you know, there are some cases where if you want to do it right, and if you really want to find out what workers are exposed to, especially if it's, you know, something highly toxic, there's really not a good argument to skimp on something like assessment and then following up with the proper controls. So this is just some things to consider yourself with, because a worker might get a report and say, oh man, I'm fine. Well, yeah, but they came and they sampled you where you actually weren't actually doing much work with that chemical, right? It's important for them to know that. Unfortunately, like with a lot of things, if you have an expert, they can either find you something or not find you something. You know, for instance, I had to laugh one time where a home inspector was looking for radon in a basement. And I happened to come, you know, to look at, you know, the setup on behalf of a friend of mine. I just started laughing because the guy put the collection devices on the windowsill with the basement window open. And I said, wow, I'm pretty sure you're not going to find any radon here either. He's like, oh, why is that? I said, because you put it up on the windowsill with the window open. Come on. You know, and you're supposed to sample for radon in the middle of the basement, a few feet off the floor. So if you want to not find something, you know, I can help you do that. Is it ethical? No. Is it what we should be doing? Absolutely not. So just please consider this, because even though we're going to go through all this air monitoring stuff, it's still just a snapshot, one moment in time. If you're only out there for one work shift or 4 hours, how much did you really know? You could either scare the hell out of that person or give them a false sense of security, or maybe you just happen to land on the truth, but you'd never know. You'd never know. All right, what are some appropriate steps, do you think, to conducting an air monitoring survey?
I think like what Mike said earlier, the first thing you got to do is kind of get a baseline of what the air is like prior to work starting or anything like that, to know what you're already have in the air in that area prior to starting work.
So let's think about a step that you might want to do even before that, even before I get any equipment or even head to the site.
You'd have to sample materials or whatever that you're going to be using on the job, removing on the job. So I know when we started on a bridge, a lot of times I would go out and take paint samples off the bridge that are a good representative sample of what's on that bridge. So I know that whatever I'm pulverizing and taking off with the grit and putting into the air, I know what I'm dealing with.
Oh, good. And I like that you said representative sample. Can you tell me what that means?
Well, when you have a bridge that has, let's say, several coats of paint on it, I'd go to an area where everything is still adhered to the surface. So I have a sample of all coats of paint that are on that surface.
Good, good. So you want to
Just the
capture
rust and everything else. I actually have to get everything off of there. That way I know everything that I'm dealing with.
And so maybe you take, I don't know, 20 samples. Do you just go to the north end of the bridge on the left side and take all your 20 samples in a 10-foot square?
No, you really kind of got look at the bridge because you never know if something was replaced or something else was done to the bridge at a different time period. So you really got to look the whole area over. And if you do see some differences, you'd want to take samples in some of those different areas.
Good.
That way you got a good representation of what you're going to be putting into the air.
Excellent, excellent, good, good.
Hey, Bernie, don't you also have to record the type of work that's being done by how many workers and all that? So it's
Yeah,
also got to
so-
represent the task going on.
So that even goes back a little bit further to what we were just talking about. So you want to know what the work is that's being done, what the hazard's going to be, right? To start to set you up. Okay. So we kind of talked about the beginning. We got to figure out what the hazards are, what the work is. We maybe go take some, representative samples. Maybe there's a baseline involved. What else? What's at the end of this activity, this survey? What are the ending steps, do you think? So I do all that stuff. I get some results back. Then what?
Well, then you'd have to, after you get your samples of what you're going to be dealing with, you then have to come up with an air monitoring plan,
Mhm.
depending on what things are being done, where they're being done on the site, what's around the area. Do you have a school nearby? Different areas where you're going to have to set up air sampling to make sure that everybody's protected, not only your workers, but the public.
Okay. Okay. Now,
Once
let's
you
say
get your results, to find out what they are, you gotta adjust your controls as needed, PPE, stuff
Good.
like that, respiratory, engineering controls, dust collectors, whatever that may be.
Good. Okay, good. And how are you going to figure out what your results are if you have to do anything at all? What are you going to compare those to? What
Say
would
that
you,
again, I couldn't hear you.
what would you compare your results to?
Permissible exposures.
Yep.
Limits.
Yep. There's that. Yep. That's one option.
But you can do from future readings, historical data, things like that.
Yep.
Like
Good.
he's saying, when you guys, I come from different, tank industry side of the industrial, but, the bridge guys, and I seen a lot in the tanks as well. Even though they said that lead or whatever that hazard may be, chromium, whatever it is, was removed by the previous contractor. Sometimes they didn't blast it clean enough, and you may run across some exposure that ain't supposed to be in there. They didn't clean the steel good enough.
Good. Good. Yeah, that's good. Okay. So this is a general, method here. Right. So review literature, inventory, process, equipment, before you even go out there, we talked about, some examples of this. Observe and document hazards, controls, and worker activities. This is something that you would do out on a site. You could even do it from historical documents. You could do it by a phone interview. Then you're going to determine the contaminants to sample based on use, toxicity, volatility, byproducts, adverse effects. Maybe, what's going to be used and you actually have a request from somebody. Hey, can you sample for this? Identify appropriate NIOSH or OSHA methods for sampling and analysis. And this is right out of an analytical method document. And then interpret and document the survey results or your assessment results. So these are the general steps in the order that you would go in, right? You wouldn't interpret and document the survey results in the beginning, right? So we'd always kind of go in this format here. And if you're going to be making a plan, you want to have it, look something like that. All right, so the first thing is review literature, inventory, process, equipment, prior to a field survey. So prior to me going out, if you're bridge blasting, you're concerned about lead, you have an idea of what you're going to have to, come out there with equipment. kind of work that you can expect. You know, you probably have an idea of what tasks are going to produce the highest exposures, as opposed to if you're doing something like, you know, cleaning metal parts before coating or something like that, whatever it is, right? Maybe you're concerned about volatile organic exposures from chemicals from flooring installers that are using some high VOC mastics or something like that. So you got an idea up front. You know, next you observe and document the hazards, controls, and work activities. This is important because, you know, I'm concerned about what the exposure values are going to be at the end of my survey, but in my report, there's going to be a section called discussion. So let's say I have really high values, you know, whoever I'm reporting to might want to have an idea of what could possibly have produced those values. Maybe you didn't have engineering controls in place at the time. Maybe, you know, you had to switch processes from, you know, hand scraping to hand sanding or something. You want to be able to document what, you know, the site conditions are. You know, I told this example once. I went out to Chicago. I had to go out there a number of times. There was a site right outside of, oh, what's that airport I always flew into there? What are the airports in Chicago? O'Hare, Midway. There was a big HAZWOPER site, an EPA listed site. What they were cleaning up, and they were going to put a big shipping center on it. I think for FedEx or UPS or something like that. But it was a hazardous waste site. There was lead, there was arsenic, chromium, I think mercury, a bunch of other stuff. One of them was silica. So many of those standards required me to sample on the worst case scenarios. One of them would have been if it was windy out, because according to the workers out there that I interviewed, they said, yeah, Bernie, if you get up here and it's windy, sometimes I can't see, you know, 20 feet in front of me. It's so windy. So the first few times I flew out there and sampled, it was calm as could be. You know, I remember one time they're like, Bernie, if you were only here yesterday, but we can't predict the weather. You know, so the client at the time was like, why are you sampling so much? I said, because I'm trying to meet the requirements of the standard and get you some valid samples so that the person actually who's signing off on the clearance form that this site is cleaned up knows that I did so. And so finally I got out there and I was able to sample, and it was really windy. And sure enough, just like the workers were saying, I couldn't see out there. I mean, I was, you know, having to cover my eyes sometimes because the wind was whipping that dust around so much. And come to find out, I got really high exposure levels, you know, of that stuff. So it was telling us that they weren't putting enough, taking enough soil out and putting enough clean stuff down yet. So you want to be able to document, you know, what's going on when you take your samples. Monitoring is classified as either personal or area. You got a question?
Excuse me.
So, you know, you're probably familiar with this, right? Where somebody puts a pump or a sampling device on you. And you also might be familiar with something like this, where they set up a pump and a sampling collection device just in an area somewhere, you know, to see what the exposures are in that area. This is the only kind of sampling, personal sampling, that is allowed for compliance reasons. Area sampling under OSHA, it doesn't compute to compliance, but we use it all the time to find out if there's an issue that I might be missing. For instance, you know, I might set up sampling devices on 5 workers, but I put up 2 area samples to help me really, you know, characterize what's going on. Now in EPA, they, you know, require area samples. That's different than personal exposure monitoring under OSHA, but they do require this for lead and for asbestos. Also, other entities might require area sampling. For instance, the city and county of San Francisco requires that there is a dust control plan in place for any construction that's done inside that city and county. And one of the ways that you show that it's working is by taking area samples to make sure you don't have fugitive dust getting off the site. You know, personal monitoring is going to determine a specific worker's exposure. Now, I mentioned similar work groups or similar exposure groups already. This is one of the ways where I can kind of limit the number of samples I take. So if I know that everybody, you know, in the class today is all going to be doing the same job task with the same chemical, I can assume that you all are going to have similar exposures. Not exactly the same, because there's still some, interpersonal differences. Maybe your work methods are a little different, et cetera. But instead of sampling all of you, I could get away with maybe sampling 3, right? Because you're all in a similar exposure group. But for the most part, we're talking about a personal sample giving me what that one worker's exposure was on that one sampling period. Any comments or questions? Let's see, why don't we take a 10-minute break? It's 2:12 right now. Let's come back at 2:22 and we'll continue on. Sound good? Okay.
Yep.
Here, this is this is a test subject here. So CPWR actually can set up and look at different work tasks, things like that, and then do some research on controls and see how things might reduce exposures and things like that. So this here is a cyclone sampler. So they're looking at a respirable fraction of the dust that this fellow is producing from cutting these concrete blocks, and we can see that there is a vacuum attachment, but they taped it off to want to see what it's like if you're just doing some dry cutting without any kind of control. Area monitoring determines concentration at a location over time. So again, it's not personal exposure monitoring, because that personal monitor goes with that person everywhere they go. It captures, high peaks, it captures low peaks, and it averages everything out. That's one of the issues with personal monitoring, actually, is we don't know if there are any spikes in exposure. We just get a time-weighted average for whatever that time sampling was, whether it's 2 hours, 4 hours, 8 hours. But it's not going to tell us, oh, there was a peak at, hour 3 or hour 7. It just gives us one value. And area sampling is the same way. Now, it's just going to be a stationary, sample that's there. So this here was, these here were set up because they were incinerating dead turkeys. So they wanted to make sure that particulates weren't, getting off site, and to see what kind of effect that might have on neighbors for doing things like this. If you've got bird flu and you got to depopulate a bunch of birds, you got to make sure that you can do it. And there's only a few ways that they do it. You want to make sure that none of that stuff floats off to neighbors. A wipe sampling is another form of area sampling. It's not going to tell you what's in the air. It's going to tell you what was accumulated on that surface. It does have some applicability, because if I have high dust levels on surfaces, I can assume that that's going to get up into the air at some point, but I don't know how much. So what that would do is, if I had some high wipe sample values, I would want to make sure I'm doing some either personal exposure monitoring, or at least area monitoring. And in fact, we know that this is so because some of the standards don't allow accumulated dust, right? Asbestos, lead, cadmium. It's got a housekeeping statement in there that says you have to keep all surfaces free of accumulated and noticeable dust, in case there happens to be a portion of that contains lead or asbestos or whatever it is we're looking at there. So I can use this to help set up my sampling plan. Next step, determine the contaminants to sample based on standards, use, toxicity, volatility, byproducts, adverse effects. For example, if I'm looking at welding, I'm going to want to look at what kind of welding rod they're using, what type of welding process they're doing, what they're welding on. That's going to help me determine, what I'd want to do to set up my sampling scheme. So this is mostly all done, before you ever get there. And historical data can help you. Next step is identify the appropriate NIOSH or OSHA method for sampling and analysis. So one of the ways we do that is we're going to look at the NIOSH Manual of Analytical Methods. Right now they have the 5th edition. And basically what you do is, and you can find this in the pocket guide, let's say if you look up toluene, it's going to give you what NIOSH analytical method to use. And this is a step-by-step process of basically what I need to do to make sure I'm taking a valid sample. If I don't do it this way, it's not valid. So I can't use it to compare for OSHA compliance. If the, contractor or employer gets in trouble, they would not be able to use that in court. It's not going to be a valid sample because I didn't do it in this method. So this is like a general way of how these are set up. So you're going to see the pages look like this. There's additional pages as well that actually get into, correction factors, lab methods, things like that. But for the most part, as the industrial hygienist, this is what I'm most concerned about, which is the first page. Doesn't mean I don't read the whole thing, but I'm mainly going to be drawing from this first page. So we've got a chemical name, what the method number is up here, formula, all this other stuff. It's going to give us OSHA occupational limits, NIOSH values. It's going to give you some properties. And then we get into the real, the heart of this. It's going to tell you what sampler to use. It's going to tell you what flow rate or range to set it at, what the max and minimum volume it is that you can collect. How do you ship it? Very important. Some samples that you take, if they're volatile, even mercury, you got to make sure that you're shipping it cold. Because if you don't ship some things cold, it's going to dissipate or it's going to break down and you might not have a valid sample anymore. Sample stability, blanks. What's a blank? When I'm taking samples of something, what is a blank sample? A blank sample is something that I'm going to take and submit to the lab to make sure that the sampling media is not interfering and giving me, false values for my sampling, or that the shipping process doesn't contaminate it. So what I'll do, like, let's say if I'm, taking, I don't know, a VOC sample and I've got a sorbent tube. Basically, I would take a sorbent tube, I would break off both ends, and then I would just cap it, and I would fill it out that it's a blank, number one, put it in my envelope. Maybe halfway through the day, I take another one, snap off the ends, cap it up, blank number two, put it in the envelope. I don't hook it up to a pump. I don't do anything else. I just, snap off the ends. If I got a, closed cassette, I would flip around the little stoppers in it or something, identify it as a blank, and send it with my samples. The lab is going to run that as if it's any other sample. And then they're going to see if there's any characteristics of that they would have to either, take away or add to the actual field samples that I took. And again, they do it for two reasons: to make sure that that sampling media isn't adding to my sample or taking away from it. And they want to make sure that it doesn't get contaminated in shipping. Typically, it's recommended that you take 2 field blanks for every 10 samples. And the blanks will let you know here. Then it's going to tell you what the measurement techniques are that it's going to be done in the laboratory, how to calibrate the sampling devices at the lab, what the limit of detection is. What's a limit of detection? This is something that's really important. It ties in with the minimum volume of sample that I have to take. The lab equipment that I'm going to send these samples off to have a limit of detection. So there's some minimum amount that has to be in that sample for it to register. So let's say if the gas chromatography's limit of detection was 100 ppm. I'm just pulling this number out. I have to make sure that there's at least 100 ppm in that sample for the instrument to detect it. If it was 90 ppm, it wouldn't detect it. Does it mean there was nothing there? No. It means that I would get a report back that said less than the limit of detection, because they're not going to say we didn't find anything. They're just going to say whatever the sample is you sent us was smaller than what our device can read. Now, some lab equipment has very, very good and low limits of detection, so they're very sensitive, but not everything. Now, there's some tricks that a lab can do to get around that. They could say, take a bunch of your samples together if you sampled it in the correct way and you notified them that this was what was being done. And they could add all those samples together. They could combine them. And then that would increase the amount of chemical in that one sample then that they're going to put through, you know, the detector at the lab, and that can increase the amount and they could read it. However, there's still some issues with that because, you know, you don't know what part of that sample was the higher exposure for that worker, if any. So there's some issues with that. So this means that whoever's taking the samples has to do some homework. They have to assume, calculate, you know, what the exposure is likely to be for that worker, because they have to make sure that they collect enough sample volume. Now, at the other end of the scale, they have to make sure that they're not collecting too much because they could have breakthrough, they could clog filters. Has anybody here ever seen a spray booth personal samples collected?
Yep.
You know, sometimes have you ever seen the whoever's doing, you know, the collection say, oh geez, my sample's clogged up or the pump stopped working, right? That's an example of sampling where that sampler gets so overloaded, you know, you might either have the pump start to fault or it gets so much on there that the lab can't use it. So in that case, you need to take, you know, be concerned what the maximum volume is. Now, sometimes with things like spray booths, I might be taking, you know, 15 or 30-minute samples at very low flow rates because of concern about getting my collection, you know, jammed up. So this is the you know, the NIOSH Manual of Analytical Methods. And what I wanted to do is I'm going to try something here. Cool, I'm going to stop sharing the screen for a moment because I want to see if I can play this video here. You'll have to teach me how to do this and embed it. That would be cool.
Sure thing.
At some point. All right, let me see if this will work. Get back to Zoom, share screen.
If there's sound, make sure you choose the button that says share computer audio.
The National
Can you hear?
Institute
Can you guys hear that?
Yep.
of Occupational Safety and Health announces the release of the 5th edition of the NIOSH Manual of Analytical Methods, commonly known as MMAM. Since 1974, MMAM has been a trusted tool for occupational safety and health professionals, industrial hygienists, researchers, and laboratories. It provides a comprehensive collection of methods for sampling and analyzing contaminants in workplace air, on surfaces, and in blood and urine of workers who may be exposed to hazards on the job. The manual is also valuable in monitoring emergency workers during and after their participation in disaster response situations. NMAM methods for this edition are selected based on priorities identified in a joint NIOSH AIHA survey of accredited industrial hygiene chemical laboratories. They have been developed or adapted by NIOSH or its partners and evaluated using experimental protocols and performance criteria. The MMAM 5th edition is completely digital. Users can access it on desktop computers and mobile devices such as a tablet or smartphone. The digital format provides immediate access to a wide variety of information and documentation, including links to chapters, backup data documentation, and earlier MMAM editions. There are multiple options to search for methods. Search by chemical name, chemical cast number, or method number. The digital MMAM automatically updates as new information and methods become available. A webbook is also available through the MMAM website. You'll find the MMAM 5th edition and more detailed information at www.cdc.gov/NIOSH/MMAM.
All right. All right. So this is a tool that you should become familiar with, especially if you're doing, you know, you're teaching classes like in lead, asbestos, things like that, or HAZCOM. you can get a lot of information from this. So, you know, you can make sure that, you know, you're double checking, making sure that appropriate monitoring is being done. You can ask, hey, you know, what are you using to collect the sample? What's the method you're using? They should be able to, you know, they be able to tell you. Now, the method number, you can also find that, like she said, in the different tabs of how you can look it up by either chemical name, CAS number, or method number. This is located too in the NIOSH Pocket Guide, but it's pretty easy to find stuff. And again, I use this all the time. If somebody is not collecting a sample for one of our members by using these methods, it's not a compliant sample and it's not going to be a valid sample. You know, you heard, you know, the speaker there, you know, reference how they put together these methods. It's with, you know, generations of scientists who do occupational health and safety studies. So, you know, I can't emphasize the importance of this enough. Sampling duration depends on the method, you know, that we just talked about, to be used, instrument, detection limits, concentration, and exposure limit. So, you know, I might be taking an 8-hour PEL. I might be concerned about what a peak is, so a short-term exposure limit. So then I have to try to figure out by talking with the worker, hey, you know, when do you think your worst exposure is? I'm going to come back and sample you for 15 minutes, try to capture that. So, you know, it's going to depend. So that's why we want to develop a plan to do this. So we're, you know, not doing guesswork when we're out there at the site. Sampling, as we said, could include, you know, include worst case scenario or typical exposures. Aerosols, so an aerosol, you know, I've mentioned this before, it's got a specific definition, and an aerosol is anything suspended in a fluid medium. So it could be a solid particulate suspended in air. It could be a solid particulate suspended in water. It could be a, you know, a mist or a liquid droplet suspended in air, like with our COVID, when we cough and sneeze, right? That's an aerosol. But typically, you know, we're concerned about something that's suspended in air for worker occupational health. Active sampling uses a pump to pass, you know, the contaminated air through some kind of media collection device. And there's a bunch of different kinds of pumps out there. These smaller, tinier ones are low flow pumps. So they'll, you know, either operate at milliliters per minute, maybe top out at a liter per minute, a very low flow, to some of these larger ones. In fact, you can see them, this, you know, they're bigger than what a car battery would be like. Those are high flow 20 liter per minute pumps and beyond. You know, there's a bunch of different brands, types, you know, that are available. Pumps have to be calibrated before and after sampling. Has anybody used one of these devices before? This is called a dry calibration. So the old school method, we'd have to use a soap bubble. So we'd have this cylinder, this burette that was marked out for volume. And we would suck up a soap bubble in it and hit a stopwatch. And after it went so many milliliters, it hit the stopwatch and we calculate what the flow rate was. And that's how we could calibrate our pumps. Nowadays, though, we've got these dry systems where there's this little frictionless weight in here. And, you know, it's basically drawn up through the pump when we're adjusting our flow rate on the pumps, make sure that we get what we want, you know, a liter per minute, 2 liters per minute, whatever. And these are valid primary standards. So the difference between a primary standard and what's called a secondary standard is these are definitive. We know there's no error or mistake in these. A secondary standard, has anybody seen like a rotometer or a flow meter? It looks like a little, you know, device that you could stick on a pump out in the field and a little bubbles going up and down inside of it, right? Sometimes you might have those on, you know, compressors and things like that. But those secondary devices aren't valid. So I wouldn't use one of those, you know, and say, hey, I made sure that all my pumps were working out in the field with a rotometer. If I were to say that in court, it would, you know, would be thrown out. So you have to make sure that you're calibrating these things before and after sampling. Why do I need to do it before and after? Let's say my sampling method says I've got a range between 1 and 2 liters per minute. And I can turn that pump way past 2 liters per minute, or I can turn it lower than a liter per minute. but my range is 1 to 2. So in the
Make sure you're
beginning,
getting a, would that be to make sure you're getting a accurate sample?
yeah. So I want to make sure that if I'm running it at a liter a minute, it's actually 1 liter per minute. So on my pumps, there's a little rotometer here. So it actually, this might be a liter per minute. This might be 2 liters per minute. This might be 3. This might be 4, whatever. I can't count on this to be a true value. So if I want it to run at a liter per minute, I need to use a calibration device to make sure it's actually running at a liter per minute. And, what happens with these is there's a little, this one here, I think it's on the top, this pump over here. If I take the screw out, I can move this cap off. There's a screw in there that I can adjust the pump higher or lower. So I adjust it to whatever it is that I want. And then what I would do is I would actually take 10 samples in a row. So like I would just hit the button 10 times and it would average it out for me. And I would take that average for what the flow rate is. So that's before I go out and sample. Why would I calibrate it again when I come back after my sampling is all over?
See if it's off or anything, you get any false readings.
Yeah, to see if it's off. I might have loaded up the filter so it's not able to draw as much air through, and that, diminishes the pump. Maybe my battery starts to go down, so I'm not drawing at the same 1 liter a minute I thought I was in the beginning. Maybe the pump turned off and faulted altogether. I got to make sure, because if I am collecting 1 liter a minute and I sample for 60 minutes, that would be 60 liters. So that's what I would tell the lab that I collected. So then they could calculate the concentration. If I think I sampled for 60 minutes, I collected 60 liters, but it was actually, 30 liters, my value is going to be half off. So I have to really make sure that I collected the right amount of volume that I told the lab I did. So I have to back myself up. So I have to calibrate before I sample and then after I sample. And if you don't do that, you do not have a valid sample. I could not defend that in court. In fact, there's some other methods that we have to use to make sure we're collecting a valid sample. There's something called the ideal gas law. And basically what it does, it says that temperature is going to affect volume, and temperature is going to affect pressure. Pressure is also going to affect volume, and pressure is going to affect temperature. Like right now, if I get in my vehicle, it's got like an automatic pressure gauge in there for the tires. And I live in New Hampshire. I don't know what it is today, like 25 or 30 out. It's going to say that the pressure of my tires is low. It's going to say it's like 20, 26, 27 PSI. After I start riding on that in that car for 10 minutes, it's going to say that my pressure is 30. What happened? Did I add any more air into the tires? No, what happened?
They warmed up.
Yeah, warmed up. I heated up that gas, whether it's nitrogen or air. I heated it up. So it's going to create more pressure. Those things happen when we collect air, right? Because we're drawing air through this pump. So when I'm calibrating these, I want to try to calibrate my pumps at the job site. Why? Well, what happens if I'm sitting in a nice climate-controlled office or lab and it's 70 degrees in there? And I go out and it's Chicago in winter and it's 10 degrees. That's a big difference in temperature. So is the volume of air going to be different collecting it out in that 10-degree job site compared to when I calibrated it in my 70-degree office?
Yeah, it's gonna be totally different.
Absolutely. And what we find, because I had to do some calculations for this, is that if there's a difference of 20 degrees Fahrenheit, you're going to have a statistically significant difference in results. There was a case that I was involved with as an expert witness for the Steam Fitters and Plumbers Union out at Hanford, Washington. and it was for the tank farms. And there was a long story. There's overexposures of these workers for decades. Finally, the plumbers and steam fitters had enough. The state of Washington had enough, and they sued the Department of Energy. I got the judge to basically consider that the thousands and thousands and thousands and thousands of air samples that the contractors and DOE took were invalid. Because they were saying, oh, we took all these samples, there's never an overexposure. Well, I said, well, wait a minute. You were doing your calibration of these pumps. Did you calibrate them? Well, yeah, they did. By the way, they didn't necessarily have the records that they did it. But I said, where'd you calibrate them? Well, we calibrated them in our office. Well, their office was 68 to 70 degrees Fahrenheit. And on the job site, if it was the summertime, it was, 100 to 120. If it's in the wintertime, it was in the 20s or 30s. You guys didn't collect valid samples. And the judge said, apparently they did not. So you want to make sure that whoever's doing your sample collection is qualified to do so, and that they're doing it in the right way. Now, I can skip these steps. I can be lazy about it and not do what I should, but that's not going to give me an accurate or precise value. And that's not doing, a worker anything. That's not helping the worker out, that's for sure. So we want to make sure that we calibrate before and after sampling, and that we do it at the site of where we're going to sample, if possible. If not, there's actually a calculation that I can use, that ideal gas law, to adjust my volume of air if there's a big temperature difference. It's a pain in the butt, but if I don't want to be out in 5-degree weather, or if it's so damn windy out, and this has happened when I was out in Chicago taking samples, my papers were constantly blowing off, so I had to put a brick on top of them. Well, that wasn't very useful for me every time I had to write something down. So I ended up just scrapping it one time, and I just went indoors and I did all the calculations. But it's a lot longer to do that, and I can also make a math error. Anyway, so you want to calibrate it before and after you sample. Cyclone sampling devices are used if we're concerned about particle size. We could sample for vapors and gases using these sorbent materials. So you might have seen these. They basically look like these little, sticks that are made out of glass, and they have some different type of packing material. And in between that packing material is going to be some kind of sorbent. So, here's an example. I've got packing material. I got some sorbent, more packing material, more sorbent. And this is what's going to collect that sample that gets sent off to the lab. They're going to strip that off, and they're going to be able to determine how much chemical is there. These here would be an example of active samplers. So I'd have to hook these up to one of those pumps. This is an example of a passive sampler, a dosimeter badge. Has anybody seen one of these or wore one of these before?
Yes.
Yeah, okay. What kind of job did you use it on?
A pharmaceutical company that required special coatings, and they made nuclear medicine, and you were required to wear these the entire shift.
Yeah. Okay. Yeah. So recently there have been some approved NIOSH and OSHA methods for exposure sampling that allow these. And instead of having a pump draw the air through, it relies on what we call a concentration gradient. So concentrations will flow from areas of high to low. So basically in our dosimeter badge, it's a low concentration. It starts off at 0. So if you're walking around, based on concentration gradients, your natural air currents, you're moving around, that chemical is going to basically deposit on this. And we're able to get a volume, okay, based on a time that this is open to the environment. So what happens is, if you're going to have one of these, you probably remember that, whoever put it on you was going to write down the time, and you start 7 a.m. And then you're going to come back from lunch, 11 a.m. They're going to write that down. So that was 4 hours of exposure that this was open to the environment. So that's how they calculate what a volume would be for this. The active sampling is going to use a pump. And they're going to have very low flow rates for these compared to things like collecting for dust or asbestos, lead, things like that, because we don't want to have any breakthrough. So there's an issue with these. And again, I wish I was in the classroom because I would draw this out on a whiteboard or easel paper. We can see here that there is packing, there's sorbent, packing, and then sorbent in this one down here. Actually, you know what? I'm going to make a slide for this. Note to self. As I'm drawing air in, this chamber here with the sorbent is going to collect chemical that's in the air that I'm concerned about. What happens if chemical is detected over here? Because this is the same material. But when I send this off to the lab, they're going to analyze this chamber, and then they're going to analyze this chamber separately. Why do they do that? It's to look at what we call breakthrough. If this chamber gets so overloaded that it can no longer hold that chemical, and it starts to be collected in this sorbent chamber, it means I had breakthrough. If that's the case, I have no idea if more chemical broke through here and went out the pump. So I actually don't know what that worker's exposure is. That's why it's really important for whoever's conducting the sampling to do their homework, talk to workers, find out what process is going on, and make a good estimate on what the exposures might be, because then they're going to set that pump's flow rate low enough so that they're not going to experience breakthrough. Because if the lab detects chemical in this breakthrough chamber, that whole sample is gone. It's thrown out. So you just wasted the whole day sampling. Now, does it happen sometime because of miscalculations? Yeah. But if you do your work ahead of time, you should be able to prevent breakthrough, because that's going to waste the whole day sampling. So that's why we usually take samples for gases and vapors at much lower flow rates, so that we don't experience breakthrough in those collection devices. So what do we do after we collect the media? We collect our sample. What happens next?
You'd have your chain of command and you'd send it out to place to analyze it.
Exactly. So we're going to send them to an accredited laboratory. There's a NAVLAB, which is a National Voluntary Lab Accreditation Program. I think that's what NAVLAB stands for. And then there's AIHA, so the American Industrial Hygiene Association. They also give accreditation to labs to make sure that they're doing a good job and that they are precise and that they're accurate. Now, I've used the word precise and I've used the word accurate. Are those two words the same, or do they have different meanings?
Different.
Different. How are they different?
Precise, I would think, tells you exactly what you have. And accurate, you could say accurately whether something's bad or okay, or
Could it be accurate
the
with the
information's real.
range?
Almost. Both you guys had a piece of the puzzle. So we'll go with Nuno's first. So precision gives us a range. So if I shot oh God, that's not going to work. Oh, it will. If I shot an arrow at a target, I shot 4 arrows. You see the 4 X's? That's precise. If I tried another 4 arrows, and that's what my target pattern looked like, that's not so precise. If I shot 1 arrow at the target, I hit the bullseye, that's accurate. If I'm an Olympic athlete for shooting, and that's what it looks like, I'm accurate and I'm precise. So accuracy is how close we are to the truth. In this case, how close we are to the bullseye. Precision is how reproducible we can be. So how many times we can reproduce that same, value. It's William Tell being able, or Robin Hood splitting their arrow in half. That's damn precise. And if it was Robin Hood, accurate as well. So,
So in other words, accurate, you're on the money, precise, you're constantly on the money.
exactly. But you can be failing and be precise too. So you can always be precisely off the money, right? So you could always be missing the mark, like this example here. So I didn't hit the bullseye here. I keep missing the target, right? So, or I should say, actually, let me do this. I'll circle what I'm talking about. So here I'm pretty precise, but I'm not accurate, right? In this example, if I look at all of my shots, I'm not accurate at all, and I'm not precise because they're all over the place. So precision is how often you can reproduce that value. So let's say, Nuno, if you're, I don't know, let's say if you're coating a wall with a VOC and it's the same kind of area, maybe you're doing hallways. I should be able to come if I'm good at sampling. If I do it the same way, I use the same pump, everything. Day after day, I should be able to get somewhat the same value. As long as your work method is consistent, but you're always in a hallway, you're using the same kind of roller, same kind of paint, it's got the same volatility, it's the same temperature, et cetera, right? I should be able to reproduce that value pretty good, right? Maybe it's always 100 ppm. I should be able to get 98, 100, 101, 97, 100, et cetera. That's precise. Whether or not—
I have a question about that, Bernie.
What's that? Yeah.
Would that be the equivalent, or would that be the definition of historical data, so that you can keep on reusing up to a year?
So historical data, we still have to determine if it was collected in a valid method, and then we could look at it whether it's, precise and accurate. Just because it's historic doesn't mean it's precise and accurate, but historic data, somebody's going to have given an opinion on it, right? Like, let's say if I'm concerned about worker protection, I'm going to look at historical data that might be presented by NIOSH or OSHA or AIHA to help me figure out what's going on. Let's say if I have historical data that was presented by, I don't know, John Mansville, and it's concerning asbestos, I might be a little bit concerned about if that was accurate and precise. You know what I mean? So you have to look at where the study's coming from and where the data is coming from.
Now, where would you classify like the manufacturer historical data? Like with silica, let's say they have documentation, and like USG has a what do they call it, dustless +3 mud, and they gave you pretty good numbers that you could use for as far as silica compliance. So would that be acceptable historical data coming from directly from the manufacturer?
So if something comes right from the manufacturer, I always look at something with a grain of salt, again, because they've got, employers, manufacturers, and labor, they're different, right? A manufacturer wants to show the public that, hey, our stuff is safe, it's good to use, et cetera, et cetera. Or, maybe they go a step further and say, hey, this is how it's safe to use. If you use it in this fashion, it's not as safe. So it could be. What I would do is I would look at how they collected their data and what they use to produce that data. And then from there, I would be able to make an opinion, if I compare it to other groups that would have done something similar, if they were, legitimate or not. That's a good question. You always want to know where your data is coming from, because again, if Ben & Jerry's writes a report that says Ben & Jerry's ice cream is the best tasting ice cream in the world, okay, well, how about if I collect that data a different way? What if I just, take samples of everybody who lives in, the state of Arizona, what they think about Ben & Jerry's ice cream compared to Breyers or Blue Bunny or whatever, right? So you got to look at where the data is coming from. So what I would do in that case, was a company called USG?
Yes, they do have between 6 and 8, I believe, micrograms per cubic meter for sanding.
Okay, so what I would do, David, is I would look at USG's data, and then I would see if maybe NIOSH did a similar study, maybe if the American Industrial Hygiene Association did a similar study, maybe a worker advocacy group like CPWR or something like that did a study, and I would look at all those together, and that's one way that I would be able to tell. It's a lot of work, you know, but if our ultimate goal is to make sure that we're doing the right thing to protect the worker, that's what we're going to do. So that is an excellent question. You know, look, I hate to say it, but this is sneaky of manufacturers. If you look at like manufacturers of, you know, products that might contain asbestos, what you'll notice is they have to put it on the label, but they might label it as mineral fibers. It doesn't say asbestos. It says mineral fibers. Are they doing something illegal? No, they're just using a term that the general worker might not identify with. Well, mineral
Also,
fibers. That sounds
also, what's the definition of trace? Because also sometimes you might see trace. They don't give you an amount. They just say trace.
exactly. Exactly. And there are definitions for that, but you'd have to go and look it up. And then, you'd have to communicate that to the worker so they can make a determination if they feel comfortable with that, right? So these are all very good questions. This is the way that you can lie with data, right? That's why we really want to know what's behind the numbers. And that's, as an industrial hygienist, that's what I try to do. And as an industrial hygienist that likes to do training, or all of you that like to do training, right? We try to pull back the curtain of what those numbers mean. Mike, did you want to say something? No?
No, I'm good.
Sometimes people's like their boxes highlight in yellow. I always think people are talking.
Yeah, I was coughing.
Okay.
I thought I was muted.
All right. So good questions. Let's keep going here. We got a few more slides. So analytical methods can be qualitative, quantitative, or both. So basically qualitative is whys, hows, whats. Quantitative is how much, how often, how much. Not necessarily assigning numbers, but we can assign numbers with more, comfortability. So we're more comfortable that the numbers are valid. Sample size, usually smaller populations compared to taking larger sample sizes. I often use the law of large numbers. So I know that I'm going to be more accurate, more precise, and closer to the truth if I take lots of samples. If I'm only taking one sample on any given day, I'm rolling some dice. Data collection could be things like interviews or focus groups compared to actual surveys that collect information, simulations, things like that. In data analysis, there would be a non-statistical method compared to a statistical method. So have you heard the phrase, oh, this is good within one standard deviation? That's a way that we can promote statistical analysis to our samples. So that's an example of quantitative data compared to qualitative data. They wouldn't use comparisons of standard deviations, whether it be 1 or 2 standard deviations from what the average is. All right, we're just going to run through a couple of devices. I'm not going to get into these in too much detail, but I just want to let you know what these things are. So gas chromatography is often used to sample for gases and vapors. So if we collect gases and vapors in those little sorbent tubes, those glass tubes, that's what would be used at the lab to find out what the amount of chemical was out there. And it's going to be referenced to in those NIOSH analytical methods. They'll let you know what the lab's going to use. So this is what these devices look like. Basically, it's an oven that has a detector in it, and they're going to inject the sample into this, and it's going to go through a long process. It's going to go through a tunnel, basically, and then it's going to come out the other side of the tunnel, and magically it's going to appear on the screen and lets us know what the concentration is. This is kind of a schematic of what this looks like. So you're going to have to carry your sample on some kind of inert gas. So they select a carrier gas that will not interact with your sample because that'll poison it. So they're going to inject it, and it goes through this column or tunnel. And these columns can be, they can be miles long, some of these things. This is an example of a very small column that's wrapped around and around and around. They can be anywhere from a few feet to, you know, hundreds and hundreds and hundreds of feet that are just coiled around. The longer the column, the better separation you're going to get of your sample. And there's a bunch of ways that we can kind of manipulate this process. In the column, there's different packing material. Think of it as a tube of toothpaste, if you would. And that packing material is going to grab the chemical on its way through. And it's going to be shot through in pressure, and it's going to be heated. And based on the column's material and what the sample is you're running, it's going to hold on to it and spread it out. And this is really beneficial if I take a sample and you might have 5 chemicals that you're exposed to. I can guarantee that if you're working with, you know, coatings that are VOC based, you're being exposed to more than one VOC. It's not just going to be one thing. But you're not going to know unless we can separate that out. And this device will do that. And what happens is as they send it through, it takes some amount of time for the sample to run through the instrument. Based on when it comes out, what time it comes out, they're going to be able to identify what that chemical is. We call that retention time. And the reason why this will work is because this is a test of knowns. I have to know what I'm looking for. So Mike, if I know you're, you know, using a certain paint and it's got acetone in it and maybe xylene in it, I can tell that to the lab, and I'm going to collect a sample for xylene and acetone. And the lab says, okay, I'm going to run a calibrated sample of acetone and toluene through my equipment first. I'm going to see that those come out at certain times. So they know when toluene comes out. Maybe it comes out at this peak, and they know acetone comes out at this peak at their different times. Now I take your sample, Mike, and I run it through, and it's a mixture of toluene and acetone. I see that there are 2 peaks, and they're going to be at the same exact times when I just ran the individual standard samples through. I've got it. I know what they are. One of those is toluene, one of them is acetone. And then the amount under this curve here, that area is going to reference concentration. So the bigger that curve is, the more contaminant is there. And that's how they determine these samples through a gas chromatograph or a liquid chromatograph. And they come out with these charts that look like this. And sometimes they look really messy. I can show you examples where you've got many peaks that are very close together. And it takes a real, expert to kind of delineate what these chemicals are, because they're not separated. They kind of overlap each other. Again, though, a chemist could use some technique. They could change the column. They could maybe heat up the system. They could cool down the system. And that might allow those chemicals to separate out as they're going through that long column. Liquid chromatography is something similar, but we use it for liquids that have low vapor pressures. And it's going to do the same thing. It's going to produce a chart just like I showed you. And they're going to do the same thing. They need to know what chemical you sent them. They can't just take a sample and say, oh, I'm going to figure this out. That's not going to work. They have to, if you're sending them a sample of methylene chloride, they're going to take standards of methylene chloride and run those through their system first. And that's going to help them standardize and calibrate their system. And then they'll run through your samples of methylene chloride. And then they're going to be able to get you some results. But if you just send them a sample and don't tell them what it is, they can't use this. They're not going to know what it is that they're looking for. These are a couple of examples of low vapor pressure chemicals that a liquid chromatography could be used for: amines, bisphenol A, and pesticides. Mass spectrometry is used with a gas chromatograph or liquid chromatograph to be able to determine what it is. This is more expensive. So sometimes I might take a sample and I say, look, Mr. or Mrs. Lab Tech, I'm going to be taking the sample. Maybe it's in a dry cleaning facility. I know that they use these chemicals. There might be other chemicals there that they're not documenting. Let's figure it out. So they say, okay, send us a sample. We'll run it through under gas chromatograph, and we're going to attach a mass spectrometer to it. And it's going to be able to identify 100 different chemicals that we think would probably be in your sample. Great. So I can have them do that. Same thing would work with any of our IAPA team members. Maybe you're working with a bunch of different coatings, and we want to figure out what's in there. So I can say, look, I want you to sample for, VOCs within these molecule ranges, and then tell me what's there with your mass spec. Okay, we can do that. It's going to cost more money per sample, but it might be worth it. So there's some ways that we can kind of get around unknowns if we don't exactly know what you're being exposed to, but we have a hunch. We can handle that, but it's going to cost more money. As my dad used to say, you can't get something for nothing. That's why I believe in a union pay scale. If you want good work, you need to pay for it, right? You can't get something for nothing. Atomic absorption spectroscopy is a way that we would analyze for metals. So when you're taking your worker lead samples, they're going to send that off, and it's going to be analyzed by an AA, or atomic absorption spectroscopy. Kind of does the same thing, where they're going to send it through this device. It looks very exciting, just like this. They're all a bunch of boxes. This one, has a vapor hood here and a fume hood, because they want to capture this, because it's going to send it through, it's going to burn it, it's going to destroy the sample. And as it's doing that, the detector is going to be able to pick up if it's got that chemical you're concerned about, and it's going to give you a reading. And then that chemical basically gets burned off and it goes up the vent there. You can look at inductively coupled plasma atomic emission spectroscopy. Say that 5 times fast. I dare you to say it 5 times fast after you had a few margaritas. It's a long word, but this is what we use if I send a mixture of metals. So maybe you are concerned about not just lead on your bridge, but maybe lead, antimony. Maybe there might be some cadmium on there if they use some anti-corrosive paints in the past, whatever. So you send that sample off. They can use inductively coupled plasma to be able to determine multiple metals in that one sample. This is very expensive. AA, if I'm sending it in for lead, might be $35, $40 a sample. If I'm sending in a sample of mixed metals, I might be talking $300, $400 a sample to do that. So it's a big difference in cost. That's why doing your homework is so very important. Not just to make sure that you're capturing the right stuff, but I can probably knock off some lab fees. I'll tell you, I've done hundreds of exposure assessments. All the time, the bulk of the cost of me doing that is not my labor. It's not that I didn't bill myself out, at a reasonable cost. It's just that the lab fees are usually 2/3 the cost of any assessment that I would do, because lab fees are very expensive. We can use a microscope to identify some stuff, right? You're probably familiar with this from either identification of mold samples or, asbestos. So here's an example, just of basic light microscopy here, like this microscope over here on the right. This one here is transmission electron microscopy, like this one here on the left. So this is a really nice, clear example of, TEM asbestos samples. You can see the difference in clarity, right, between one that's just light microscopy and one that's TEM. Much, much smaller and clearer pictures. Gravimetric, so now I'm talking about looking at something by mass, right? So I can look at a silica sample by mass, right? Or a total dust sample by mass. We have a PEL for that. In that case, I need to make sure that I am pre-weighing my sample and that it's post-weighed. The pre-weigh is going to tell me how much my collection, sample weighs, or I'm going to also what we call zero that out. But I have to do it in a controlled chamber because moisture is going to affect this a lot. So what they do is they basically put all these samples in a climate controlled chamber. They will measure them and zero them out. They send them off to you in the field. You take your sample, you note your environmental conditions, you send it back to the lab. The lab puts your samples back in this chamber. They wait 24 hours. All the humidity that was collected on that is going to be dissipated. And then they can find out how much of a sample you've got there. All right, any comments or questions? Those are all active, samples where they have to collect something on media or passively collect sample on media, send it off to the lab, you wait, you get the results back. Any comments or questions? All right, just to sum up, so you can only collect compliant samples if they're full shift and if it's done by the NIOSH analytical methods. It's the only way that we can do that. Now I'm just going to quickly cover some direct reading instruments for gases, vapors, and aerosols. So these are something that can give you a result in real time. You don't have to wait for the lab to come back. Now I can get values back in 24 hours if I want from the lab, but let me tell you, that's usually at like a 500% markup. Typically they take 2 weeks to come back. You can have them come back sooner, but you're gonna pay for that. So advantages of direct reading instruments: you can get instant results. They're pretty accurate, and you can get some that are specifically for certain chemicals as well. How about some disadvantages of direct reading instruments? First off, how many people here might have used a direct reading instrument before on the job?
We use, for breathing air, we use instruments to measure carbon monoxide in the breathing air, which is common on all blast jobs.
Mm-hmm. How about anybody ever do any confined space entry work? You would have a direct reading instrument associated with this for sure. Basically, it's one that just tells you oxygen level, right, and carbon monoxide level and LEL. And it gives you the results in real time. So these things are typically pretty expensive. Like a photo ionization detector is anywhere from $1,000 to $5,000, depending upon what kind of bells and whistles you want it to do. Some of them have limited accuracy. So they're going to give you results right away, but they might actually be farther off from the truth. Typically a lot of these have, accuracy issues of up to, plus or minus 5%, which means if the true value is, 100 parts per million, the result that you're going to get could be 95 parts per million or 105 parts per million. That might be acceptable. That might be fine for whatever it is you're doing. You need to know the contaminant in most cases. Like a PID, like I mentioned, it's going to give you one general value. You might be working with a VOC coating, and you might have 10 different chemicals in there that are volatile. But the PID will not tell you a value for 10 different chemicals. It's going to give you one value. And you got to figure out, well, what's the chemical that's, most of this value that I'm getting? You're not going to know. They can have interferences, and then you still have to calibrate these things as well. So there are some issues with these, but I always have used a combination, of direct reading instrument and, collecting actual samples to send off to the lab. Direct explosive or flammable atmospheres require a combustible gas meter. You might have seen, something like this one up here on the right, where it's a combination meter that has oxygen level and LEL on it. Or you might have, or you might be used to something like this, where you're going to be just looking at, combustible gases and oxygen. Advantage: it's general purpose for hydrocarbons or combustibles. Again, it won't tell you what's flammable. It's just going to tell you that whatever is there is flammable at what level. It's fairly accurate over most of the range that it has, and it's unaffected by temperature and humidity. Disadvantages, as I said, it's not specific. You have to have oxygen for it to work properly because it's going to be combusting whatever that is inside of it. And you can tell by looking in the manufacturer's manual. There was I don't know if it was a Texas Instruments one that I used. where it said that if the oxygen level was 12% or lower, you were going to get inaccurate LEL readings. And that was a concern because my group that I was looking at had supplied air. So I wasn't worried that they were at low oxygen, but I was worried if they were going to have a potentially combustible or flammable atmosphere, because the supplied air ain't going to help with that, right? So I guess one thing it's important to understand, anytime you're going to be using a device like this, you want to get that manufacturer's manual, and you want to read it cover to cover, and you want to understand it well. Okay, it's going to have a lot of specifics for that device in there. And if you're using, these for combustible atmospheres that might contain chlorinated hydrocarbons or tetraethyl lead, they're not going to be very accurate for those as well. Measuring gases and vapors in real time for toxic concerns, you can do it with a couple of different devices: a photoionization detector or a PID, a flame ionization detector, colorimetric tubes, portable gas chromatograph. So that big, refrigerator looking device that I showed you before, they actually have one of those that's portable, or a multiple gas meter. So just quickly, we're going to go through these things here. So a PID, what it's going to do, it's going to be looking for ionizable gases or vapors. And it's going to have a wide range. And again, it's going to give you one value. It's if you've got 5 ionizable vapors and gases that might be coming off of a coating that you're applying, it's not going to tell you individual values. It's going to give you one value for all of those things mixed together. So it's non-specific. That's a disadvantage. The response to it can vary by contaminant, and it can be affected by humidity, and it doesn't detect methane. So CH4, methane gas, it will not detect that. And basically what's happening is you've got this lamp, and it's going to be exciting any chemical that's in your sample. So it draws it in through a pump, it hits it by the lamp. If the lamp energy is strong enough to excite that chemical, it kicks off electrons, and then it can be detected by its detector. So that lamp energy is very important. Example here, this mini ray system that I've used often, it's got a lamp energy of 10.6 electron volts. I have to know what chemical I'm concerned about, and I have to look it up and determine if the electron volts of that chemical is less than my lamp. Here I give an example of benzene. I looked it up in the pocket guide. It shows that it's got an IP, an ionization potential of 9.24 electron volts. This is less than my lamp energy. I know that my lamp is going to be strong enough to excite that chemical and give me a reading. If it's not strong, like you could find a chemical here that has an IP of 11. I wouldn't be able to use this because that lamp's not strong enough. So again, you can't just grab one of these and go. You've got to do some homework before you go out to the site. That's why it's really important to have qualified people to do this, or well-trained people to do it that makes them qualified.
Hey,
Yes.
Bernie,
Yeah.
what if the chemical is at the same number as the actual lamp?
Oh, you're tossing dice. It might be accurate, it might not. So that's a tricky one. So as a rule of thumb, I always make sure that my lamp is above what it is. There have been some times where I've come where it's been within a couple of tenths of a point there, and the results, they're not precise. So they might be 100 one minute, 110 the next minute, 90 the next minute. They go up and down. So it's not as precise as I'd like. So good question. So go big or go home on this kind of thing. So make sure that your lamp is going to be sufficient. Now they make lamps all the way up to 12 plus, but they're more expensive and they don't last as long. These lamps have a shelf life, just like any bulb that you got at your house. These things have a shelf life. Good question. FID kind of does the same thing as a PID, except instead of an ionization potential, because I'm using flame to excite the chemical, it has to be a flammable chemical. It won't read chemical if it's not flammable. So anything that's a combustible hydrocarbon, it will look at. Accurate over its range, again, it's going to give me one value. So if you've got 5 combustible chemicals that are coming off of that coating that you're applying, it's not going to give you 5 different values. It gives you one value. And it's a mix, it's all those things mixed together. Disadvantages here, kind of the same thing, non-specific. This one requires oxygen. Why? Because it's burning what's in the atmosphere. And it's not recommended for chlorinated solvents. It won't give you an accurate reading. Colorimetric tubes indicate concentration following a reaction. Has anybody ever here tested their pool water? You know, with those strips, you dip it in the pool, you know, this is the same thing. It's going through a chemical reaction, and it's going to let you know what the concentration is of those chemicals. It's either in a percent scale or a ppm scale. Has anybody used any of these before?
We use it for testing salts on a bridge.
Okay, all right. So they're either going to be, you know, these little sticks, they're glass, just like those sorbent tubes that we looked at for using with pumps. You're going to break the ends off. It tells you what direction to put it into the pump. And different tube manufacturers are specific for their manufacturer's pump. So this is a Draeger pump. You've got to use it with Draeger tubes. This is a Sensodyne pump. You have to use it with Sensodyne tubes. You can't mix and match those. So what do you think some of the advantages and disadvantages of colorimetric tubes are?
Probably not as accurate, and it also isn't. I mean, it's giving you probably more of a range and not an actual number.
That's right. So you're looking at the stain on a scale. So it does give you a range. I mean, sometimes I have to take in my pool, you know, chemical strip and have my kids say, what do you think? Is it more that color or more that color? So yeah, that you're right. And they're not very accurate, that's for sure. What else? Any other advantages or disadvantages? One of the advantages is the training on using these is very simple. You know, these come with directions, they're simple to use. You either pump it so many times, either 5, 10 times the directions tell you, or you pull it back a half a click or a full click. So this pump here, it either goes back halfway or fully. And then it tells you actually how to read it. So, you know, that's an advantage. It's simple to use. It's fairly cheap. This is another example of one of these pumps. This is from MSA. You'll notice here, right, there's a bunch of different chemicals for each one of these. This here happens to be from an MSA Weapons of Mass Destruction Detection Kit. It's fun to be an industrial hygienist. I get into all kinds of trouble, all kinds of bad situations. So you'll notice it's a specific tube that I would need to detect a chemical. So lucite, I have to, if I'm detecting lucite, I gotta have a lucite tube. If I'm detecting chlorine, I need a chlorine tube. You know, if I'm detecting carbon dioxide, I need a carbon dioxide tube. So you have to know what you're looking for, and then you have to have that tube. Now, I don't know if I can see it on here. Some of these have directions on them. You can see right here, like this one here says 30 pumps. This one says 30 pumps, this one says 30. So some of these actually have directions right on them, but typically there'll be a fold out direction sheet. Some of these, it doesn't say on here. All of these detection tubes have a shelf life. So if they expire, they're not valid anymore. You can use them for training and stuff like that, and that's usually what I would do. But you can't use them to actually assess some kind of exposure, you know, exposure for a worker's work environment. Can you think of any? Okay, so we went through this. So the accuracy, actually, these aren't very accurate. Plus or minus 25% compared to plus or minus 5% or so for the other types of direct reading instruments. There can be interferences. You have to know the contaminant. You know, shelf life, if they pass, you got to throw them out. Results are subject to interpretation. And then it takes, again, like any of the stuff, a snapshot in time. So these are some things that can help you read them. You know, they should be read in adequate lighting. should be read, not be read in direct sunlight. Read the full length of whatever the stain is. And usually what I'll do is I'll take, like a piece of white cardstock with me for that day, and I'll use the same piece of paper and I will read it behind that tube. That helps get a better visual, as opposed to just, holding it up and looking at the background as your backdrop for that tube. And if we were together, this stuff would make more sense because we'd be able to do some activities with this. This is an example of that portable GC with a mass spectrometer on it. So as opposed to being something as large as a refrigerator or a small freezer, they do have one of these that is the size of a suitcase. Although it happens to be like 100 grand, it's very useful for taking into emergency responses or taking into work environments where there might be a lot of chemical use, but they're unknown. Very, very good. But something like this, you need to have a lot of training on it. Basically, you need to be, a mobile lab tech, if you would. And this is a multi-gas detector. So you might have seen some of these if you've done confined space entry or something like that. You can put a number of different chemical sensors in here, carbon monoxide, carbon dioxide, LEL, oxygen sensor, ammonia is another common one. And you can change these out, and these are very easy to use. You can look for aerosols by a direct reading instrument as well, or you can do it by taking a sample and sending it off to the lab. So these here, this is a real-time aerosol monitor. This is called the Dataram from that company. Has anybody used something like this before? Something like this would be really useful actually for IUPAT members, especially folks who are doing drywall finishing, flooring work, blasting work. I've actually used this on lead jobs where instead of taking a ton of lead area samples, I take a few and I can compare it to the results that I'm getting on this. And I can let this run the whole day. And I can see peaks and valleys during the day, depending upon, what process somebody was doing with that leaded surface. So it doesn't tell me the lead in the air, but it tells me the particles in the air, how much dust is in the air. And I can compare that to actual lead samples that I took at the same time. So there's some neat stuff that we can do, but these would be useful for IUPAT members, like I said, doing some of those trades.
Yeah, we use them for the lead jobs a lot.
All right. Yeah, I mean, it helps you because it lets you know if you're approaching a danger zone, right? Because just because the value is higher or lower on that doesn't mean you're getting that lead exposure or asbestos exposure. But it gives you a general idea you might be heading into trouble. So if I see those values going up, I'm going to want to implement different controls before I get into trouble, right?
Yeah, we use them a lot for just making sure that we're doing our job as being able to contain the environment. And like I said earlier about a school being nearby, I mean, I did a job where a daycare was right down the street. So we had to put one in between our job site and the daycare just to make sure that we're doing what we need to do to contain what we're creating. Good.
Yeah, and I mean, that kind of process is really helpful too for the employer, the contractor. It's a way to show that, hey, stuff isn't escaping the job site. So if something does happen to surrounding communities or they complain, I mean, it's human nature. Sometimes you see something going on. Oh gosh, they maybe they're producing something bad. You might get somebody that complains. Maybe it's valid, maybe it's not. But if you have something like that set up, you can help show that, they don't need to worry because nothing's getting off site. Good. Yeah, good example, Jeremy. So intrinsic safety means that your equipment is not going to act as an ignition source inside a potentially flammable environment. It's different than combustion proof, where there's actually a combustion going on inside that piece of equipment, but it's not getting outside of the equipment to act as an ignition source. So if you're using any of that equipment and it's going to be in a potentially flammable environment, you've got to make sure it's intrinsically safe. These are what these tags look like from the Underwriter Laboratory. Class 1, Division 1, groups B, C, and D. So what this is material type, likelihood of presence of that material, material properties, and temperature class. And all this stuff comes out of the NEC code, which I've got here, some examples of what these mean. But if you actually look up in the code, you can, have better definitions of what this stuff is. It's just basically its potential for more flammables to be produced. Response time with real-time monitoring. So if I have that PID and I zeroed it out in clean air and I go into an environment that I know there's a chemical, it doesn't instantaneously show me what the true value is. It takes some time. So response time is the time it takes to go from an unknown reading at time 0 to whatever that true reading is in seconds. And it's important to know, because if I'm looking at, maybe sampling a vertical area for confined space entry, I can't just unwind my hose all the way down to the bottom. I have to understand what that response time is. And I have to go down, rule of thumb is every 4 feet. So before I crack the surface, I wait 45 seconds with that detector. I open the hatch up. I wait 45 seconds with that detector, record my results. I go down 4 feet, 45 seconds, record my, go all the way down to the breathing zone, record my results, go to the floor. But each time I'm waiting 45 seconds plus the distance for that pump to draw that air up. Same thing with if you're doing emergency response. You can't just take this device and walk right into that area. You got to go slow and stop. Wait for that detector to adjust. Where can I find response times for equipment?
Probably a manufacturer sheets or whatever.
Exactly, Jeremy. In the manufacturer's manual, it'll be listed there. Calibrating, very important. I mentioned before, calibrating equipment before and after you use it. Again, you want to make sure that it's held its calibration through your entire sampling time. But there's some other things that we can do with it too. You want to zero check, direct reading instruments in clean air. If you turn it on in a contaminated environment, it's going to give you low readings after. Because let's say if you turn it on in an environment that has, 50 ppm of something, it thinks that ppm is 0. So, if you go then to conduct more measurements, it's going to consider 50 as its 0 mark. So you're going to be getting false readings. So you always want to turn this stuff on in fresh or uncontaminated air. A bump test is basically just a quick test against a known standard. Like if I'm looking for, isopropylene, right? I might use a 100 isopropylene, 100 ppm isopropylene standard. And if my device reads 100 ppm, I'm good to go. Maybe it's off by a part per million, so I can adjust that value on the piece of equipment before I go and use it. And then there's a manufacturer's calibration. So these are things that you send off to the manufacturer and let them do on their recommended timeline, whether it's annually, biannually, maybe you use the equipment to death and you have to send it in more often than that. And then air monitoring equipment has to be maintained to ensure its validity. It's got to be done by a qualified person who is trained to do such a thing. And then conducting surveys must be received. You got to get training if you're going to go and use this stuff out in the field. There's a different level of expertise that you need to be able to understand to do different processes with it. But there's a lot of stuff that, an IUPAT safety rep can be trained to do and use this stuff out in the field, to help be a first line of defense for protecting our members. Yeah, this is me. Once we start doing face-to-face classes, I'll make sure I take some real great photos of all you folks doing these activities so I can replace that mug with some of you all. Anyway, the last step is to interpret and document the survey. So I get the results in, I compare it to those historical data, I compare it to PELs, some kind of other exposure limit, an action limit, something. And then I make sure that I document it. And that's it. That's how we go and we generally do these things. Any comments or questions? All right, just so you know, there's group activities that I would do with these. What I do is I set up 5 different stations. Each group starts the activity by going to their group number station. So like if you're group 1, you go to table 1. If you're group 5, you start at table 5. I typically give 15 minutes for each station unless I've got such a big class, and I try to prevent that. I try to have, no more than 20 or 25 students, depending upon how many trainers I might have to help me do something like this, because you got to monitor these stations. I've tried this before by myself. With 20, 25 people, it's tough to do because people always have questions and it's hard to meet everybody's needs before your next group has to rotate. So, typically 15 minutes. And then once, you say time's up, you rotate clockwise, right? And these are what the stations are I would have for this course. You take a personal sampling pump and you calibrate it. So what I would do is I would select a chemical that would be a concern for those students. Maybe, for painters, maybe I would take, I don't know, acetone, maybe floor refurnishers, methylene chloride, something like that. And I would have a NIOSH analytical method document there. So they would have to look up and select an appropriate flow rate, and then they would have to adjust the pump and calibrate it. I would take measurements of a solvent with a PID. One of the ways that I do this, I take some acetone, I drop it in a 5-gallon metal pail with a cap, and I have an opening in it that can be plugged up so the stuff doesn't escape, and they can take readings with it. There's a bunch of other activities that are like that we can do with a PID. Same thing, I would take colorimetric tubes and I would create a concentration of a chemical in some kind of container and have them take examples. One of the ways we did this where we didn't have an extra container to use, we had students take carbon monoxide samples from the back of a running automobile. So one of the workers, went and turned on their vehicle, they idled it, everybody took a sample, and then they shut the vehicle off and they were able to, determine it that way. One of the groups decided to take samples at the tailpipe, a foot away from it and 5 feet away from it, right? So they were able to make up some different ways to use these. Indoor air quality investigation. So I've got some different devices that we can detect. Yes, that is a dead bird. Detect different, air quality parameters like carbon dioxide, temperature, relative humidity. So I would have a station set up to do that. And then chromatography. So you can actually have liquid chromatography paper strips, and you can take mixtures of chemicals and actually have, participants see how this chromatography strip will separate the chemical out over time. And one of the ways I did that is just by taking Sharpie markers. And if you take a Sharpie marker and put it on, put a dot of it on a chromatography strip and put it in a little bit of acetone, it's going to suck that dot down to the acetone and separate it out. And you can show students that Sharpie is made up of many chemicals. So there's, some pretty cool activities that we can do to, emphasize some of the stuff that we talked about during the class through the slides and also in small group activities. And, if we were doing this face-to-face, we would do a lot more focus on the small group activity method. So all the time you saw a question answered or it said like quick activity, we would be doing something in our groups with resources that I would have available, as well as, students being able to look up stuff on their smartphones and whatnot. Do I even need to use the term smartphone anymore? I think, can anybody get a non-smartphone? I'd like to buy that jitterbug thing. Have you seen that with the big dials? No internet connection, just phone numbers. Boy, would I love that.
I think now you just have to define the user, whether it's a smart user or not. The phones are all smart.
Probably so, right? Anyway, this is a pretty in-depth, air monitoring course, for workers. When folks get through something like this, especially if we can get the hands-on stuff in there, they're going to feel pretty comfortable, to talk to, on-site, monitoring folks, their occupational health and safety specialists, ask questions, try to figure out what's in a report, etc. Yeah, and again, if you're teaching other classes that air monitoring is a part of, like if you teach respirators, you have to pair up why you're wearing the respirator. Well, that's based on air monitoring data. Same thing with HAZCOM class, same thing with confined space entry, with lead, with asbestos. So there's a lot of, classes that you teach that hopefully, going through this course will give you a little bit more comfort in teaching some of those things. Any comments or questions? That concludes the day.
Hey, Bernie, I had a question about the class that you said that you were thinking about having, the OSHA 521. What are the prerequisites? Any prerequisites to take that one?
A good attitude, fun. So just say you like industrial hygienists. Specifically say you like your industrial hygienist. No, you just.
He's all right.
He's all right. You just come and take it. No prerequisites. It wouldn't be a bad idea if you had, like maybe, like a HAZCOM class or something like that, just so a student can have some understanding. But anybody who's on this class right here, you'd all be fine taking it. I wouldn't want it to be a student's first class, so like if you got an apprentice or maybe a journey person that, hasn't gone through all the health and safety classes you were, that might be a tough lift. But anybody who's on this class, I think you'd have a lot of fun with it. And my buddy Bruce Lippy and I developed it to be a union class. So there are a lot of hands-on activities. I mean, you actually build controls. Like one of the activities we have, I bring either like a portable job site table saw without the blade or a shop vac, and we turn it on, and students take sound measurements. And then they take sound measurements right next to it and a few feet away. And then they have some material and they actually have to build a wall. We did it so that it can be done very quickly because you have to rotate through the stations. And then they have to measure, the sound reduction from that plywood wall that they just constructed, things like that. We do stuff with radiation detectors, chemical monitoring, all kinds of stuff in it. So it's typically, OSHA bills it as a 4-day course, but when we built it for labor, we did it, 4.5 to 5 days to make sure that we had enough time to get in there with hands-on activities. And it will give you a pretty good base to go out and understand how industrial hygiene should be working on your site. The goal isn't to make you an industrial hygienist. That takes longer, but you'll certainly be able to ask questions, identify where there's a need for something to be done for an industrial hygienist, et cetera. And it will certainly give you a nice foundation for other health and safety classes that you teach. I think between Bruce and I, we've probably trained over 1,000 people in it, between the operating engineers, the United Steelworkers, and the auto workers. It's been, pretty valuable for them as far as helping them with their health and safety folks, health and safety committees, things like that. So thanks for asking, David. So if you want to do it, Nicole is the scheduling whiz, so we definitely have to do it face to face. And I can get us credit probably either through CPWR or, another. I've partnered with a bunch of different OSHA Ed centers because they like it, because hardly 521 classes never go. But, when I come to them and say, hey, I've got, a union here that wants to run 50 students to the 521, they're like, okay.
I think CPWR would be the way to go because they subsidize a lot of the cost, don't they, for us?
Yeah. And what I can do, because I know that we've got, an arrangement with CPWR, and I know, actually Gary Gustafson, who works at CPWR now, he used to be the health educate lead, the director of training for the laborers for LiUNA. I've known him for a long time, and he's the one who actually recommended me to Wayne and Jim, that got me involved. So I told Gary I got to bring him out for a nice steak once it's safe to do so. I have a rule: I'm not going to eat a steak in front of a plexiglass. I can't. So yeah, so we could do that, David. And what we could do is I could probably, I'm going to need help. I could probably get another one of my colleagues like Bruce Lippy or somebody that's in the labor field to help out with it, but I could also probably get one of us, so if you took the class, right, and if you're an OSHA ed trainer, if you liked it, you could help me teach the class. I mean, because I can't do it alone. I've always had at least one other person help me, because it's a lot of activities to do. I mean, just setting up the activities is a job for a trainer to do. So yeah, that would be cool. See, you got me excited about it. Yeah. You passed the test already. No, there's no test. You just got to come to the classes. Any other comments or questions?
Yeah, Bernie, have you ever worked with any SDS management software or anything like that?
No.
No.
No, you mean like
Think of like
to create them or to manage and catalog them?
mostly managing and cataloging everything. A lot of, I mean, I've got a lot of products up in Brentwood that, you've got all the different trades, all the different products in there, and I've got to get the building certified through NACE to be a testing facility.
Yep.
And to do that, I've got to make sure I've got all those products on the SDS and all that. And I know there's some programs out there where when you bring a new product into the site, you can scan it with your phone, the UPC code, and it automatically, puts it into the system, into the SDS system. I just didn't know if you had ever worked with any of those things before.
No, I haven't, but I'll tell you what, Jeremy, one of my goals is to develop model health and safety programs that, either a training center would be required to have, or, an IUPAT contractor would be required to have, and just have those at the IU for reference. So let's say if you needed a HASCOM program for your training center, you didn't have one, you could say, Bernie, can I grab the one? Sure. You take it and then you just, modify it to your work site, right? Your training center. You'd have to do some adjustments, but not much.
Right.
And part of this is to be able to be accredited for the different organizations that might give an IUPAT District Council Training Center accreditation in whatever it is, in this case, NACE. So I can look into that. I'll do that. It might take me a couple of weeks. I got a lot on my plate because I've got, I don't know how many classes.
Oh yeah, I've got tons of stuff still left to do on that anyways, but I did find something called Process Map. And it's got from printing regulatory labels to managing chemical information, emergency response stuff.
Yep. Accessing
SDS sheets immediately and being able to print them out, like if something happened at the facility and you had to send somebody to the hospital or whatever. But it even has permit management, industrial hygiene management, and incident management.
Yep.
So, and it's centralized. So it could be centralized at the IU and tweaked at all different facilities throughout the United States.
Yeah, that would be great.
Be able to, you'd be able to access it anywhere.
Yep.
Which is, I think, would be pretty great if that could happen.
Sounds like a great job for my future potential staff member. So what I'm going to do, Jeremy, is I'll put this though in my middle burner. What I'll do is I'll call a buddy of mine at the Steelworkers, because they their members are around tons of chemicals. I'm sure he's got some insight onto what might be a good labor friendly tool to use, and I'll come up with some examples. And maybe what we can do is, I don't want to just select one of these and say, hey, use it, but maybe if we could create like a task force of other members like yourself from different district councils and just say, hey, I've narrowed it down to these 3 things, everybody. What do you think? And then we can look through it and select it as a group, agree on it. That way there we've got buy-in, right? And then maybe recommend something like that. And then maybe we could, purchase it through the IU or something like that. Because that makes sense to have it in a centralized spot. And again, I'm sure there would be, now you got me going now. I can imagine, an administrator for each district council where, Jeremy, if you get a new chemical in that's not there, you upload it, it automatically gets cataloged, at the central database. And then that would give any member access throughout Canada and the US to it.
Yep.
Good. Yeah, good thought.
And if you can add it to the IUPAT app, that'd be even greater.
Yeah, sure. All right. Hey, you know what? You know what?
Interrupt there, 1 second. Mr. Arvayo, are you available for hire? Because you are the technological guru who I have interacted with, and I just need to know if you want to help get it on that app, because you mentioned that app and you could probably break up and whiz up an app like in your sleep. So be careful what you're asking for. But Mr. David is an amazing guru when it comes to technology and electronics when it comes to our classes. Good
Well,
resource.
not for nothing, but you know, I like to go after grants. One, because you get money. Two, it's a public good. And three, it makes us look good as the IUPAT. And we just successfully got, a Susan Harwood grant. But there's something called a small business initiative grants that are funded through the NIHS. I used to do, actually, I was part of some of these as a technical subject matter expert, but I also was on the NIHS review committee for a couple years. And what it is they're like advanced training technology or grants that you can get. And if you get it, you actually get to keep the product that you make. So I'm just thinking, David, if we made some kind of a, HASCOM, SDS app, right? And if it's new and we could apply for funding under the SBR, and they're pretty decent. The first phase is usually like 150,000 bucks to develop the app, and then you can get a second phase grant where you go and you take data on it. You actually use it out in the field and you build capacity, but you own it. It's not like the Susan Harwood grant where we have to upload, what I did to the Susan Harwood database and everybody can use it. This is something that the IUPAT would own and would trademark. They come out, once a year if you're interested. Nicole, if you could make a note to self, maybe we could, check out who might be interested in something like this. And again, it's something that's incredibly usable for our members. One of the problems that always happened with the SBIR grantees is that they would make something and then they would present it. And I would, I remember one time I was at a conference in Florida where some SBIRs presented, and I was waiting outside out of the conference hall. And all these folks keep coming out and they're like, man, Bernie, why don't they ask us what we want? These are different unions. They're like, we're not going to use that shit. So, these folks made some really nice looking products, but it wasn't usable for the members of the different unions, right? So if we made something, we know it would be usable for our members and we get paid to do it. It would be ours. Yeah, good stuff. And who thought we were just going to be talking about air monitoring today, huh? Yeah, Nicole. If you could just make a note about this, this is a great idea. Between this one and the SDS thing for Jeremy mentioned.
Yep, noted.
Yeah, Jeremy, would you be interested in being on a small committee? I'm just imagining like myself and maybe three other trainers or something.
Possibly. Yeah.
Yeah, one thing I learned is I don't do something like this on my own. Because what the hell did you select that for, Missoula? No. I want to say, oh, me and these other three folks selected that. And also, too, I might have my ideas of what might be appropriate and work well, but I don't know if it is going to be appropriate and work well for folks at the different councils in the field. So I want to make sure that it crosses all the boxes, right?
Yeah, I just saw all the stuff that I got to do with the NACE, and when I saw everything that had to do with SDS sheets and having
chemical inventory,
these different records, it was like, well, if we had like a centralized thing,
exactly,
it would probably make it much more easy for all the district councils to be able to get through this whole NACE thing, and even depending on how it goes down the road, I don't know, but just in general,
yeah,
and all that stuff at the and then training and all that, being able to access an SDS immediately and press print, send somebody off with that would be a great thing to have.
Yeah, and I mean it's going to help you, comply with the HASCOM standard because one of the requirements of the HASCOM standard is to maintain a chemical inventory, and with that, the safety data sheets that go with it. And let's say if you were used to getting, acetone by XYZ company, but they ran out, and instead you got acetone delivery of BCD company, you better have a actual SDS from that company. Otherwise, it's a violation. You've got to
Right.
have it for the manufacturer for that chemical specifically. And there's a bunch of other weird caveats like that you want to make sure that you keep up on. And it's basically maintaining that inventory. So I mean, if you can, you know,
And it has to be accessible to every person.
exactly.
Whereas if everybody has the app, it's now accessible. You don't have to have these books and all these different things all wherever in the building. You know, it's all accessible.
Unless it's somebody like me that would like to get a jitterbug phone that wouldn't be able to get it. All right. Any other comments or questions? All right, thanks, folks. So, you know, I'll look into, you know, the potential for doing a 521 class. I'll reach out to Gary at CPWR and maybe put something like this, you know, in at the end of the summer or the fall or something like that. And, you know, we would get 521 credit for it, certificate, and maybe, you know, I can bring a few people along that would like to teach it after that. And we could make it an evergreen thing, you know, because once we start teaching it, it is a phenomenally great, all-encompassing, you know, IH course for workers. You know, if they were to take it, it would certainly give them a lot more insight on what should be happening out on a job site for IH issues. So, and it's not just chemicals. You know, it covers all different rubrics: noise, vibration, heat, cold, all that good stuff. So,
It would be definitely be a big eye opener for a lot of people, I'm sure.
yeah, absolutely. All right, folks, if that's it, that's all I got. Please make sure you fill out that survey and all that business. Nicole, you got anything you got to sign us off with?
Nope. Except that I think you guys are awesome. Thanks for attending today. Have a great rest of your day and week. And we'll see you next time. Don't forget the survey.
Have a good day.
Bye, everybody.